NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Wow, we packed the house tonight. How's everybody doing? Excellent. Well, thank you all very much for, again, coming to attend these wonderful lectures. We very much appreciate them. The Cassini mission, a cooperative undertaking by NASA and the European and Italian space agencies, has revolutionized our understanding of Saturn, its rings and amazing assortment of moons, and the planet's dynamic magnetic environment. The astonishing discoveries continue to this day, and we can't wait to see what happens when Cassini repeatedly dives between the innermost ring and the top of Saturn's atmosphere during its final 6 months, starting in April 2017, before finally plunging into Saturn's atmosphere in September. Tonight, we have two guests who will present highlights, expectations, challenges, and the promise of Cassini's final year. Dr. Earl Mays is the manager of the Cassini program. A veteran of 32 years at JPL, he began his career working on the navigation and engineering teams for the Galileo mission to Jupiter. After Galileo's final Earth flyby, he transferred to Cassini as the spacecraft operations manager and then deputy project manager. He left the project for 8 years to hold management positions in guidance, navigation, and control in avionics, then returned to Cassini as the program manager in January 2013. Dr. Linda Spilker is the Cassini project scientist and a co-investigator on the Cassini Composite Infrared Spectrometer team and has worked on Cassini since 1988. Since joining JPL almost 40 years ago, her first and only out-of-college job, by the way, she has worked on the Voyager project, the Cassini project, and conducted independent research on the origin and evolution of planetary ring systems. She also supports proposals and concept studies for new missions to the outer planets. She enjoys yoga and hiking, especially through her favorite park, Yosemite, and is married with 3 daughters and 5 grandchildren. So up first tonight, perhaps one of the coolest grandmothers ever, Dr. Linda Spilker.
Thanks, Mark. That was a great introduction. And as Mark indicated, Cassini has truly rewritten whole textbooks on the Saturn system, from the planet itself to the complex ring system to these just amazing and astonishing moons that come in all shapes and sizes, and then the great magnetic field that surrounds the planet itself. Now, I'm going to cover some of the highlights of Cassini's journey in the Saturn system, her 12-year voyage around Saturn. And then Earl is going to talk about the grand finale, those last precious orbits of Cassini with truly unique science, essentially like a brand new mission, and then those final moments with Cassini. Now, if you look at the picture behind me, this is one of my very favorite montages from Cassini. And as a ring scientist, you can probably guess why. In this, you can see all of the major rings of the Saturn system. And it's a unique geometry. The planet itself is covering up the sun, allowing Cassini's sensitive cameras and detectors to mosaic this backlit view. It's kind of like looking through a dusty windshield or something, and these particles brighten up and you can see them. So what you see is the planet itself, then the main ring system. That faint ring just outside the main ring system is the G ring, and that beautiful blue ring is Saturn's E ring. And it's created by tiny icy particles that come from the south pole of Enceladus that go on to form a ring that fills Enceladus's orbit. These particles even go all the way out to the orbit of Titan, one of the distant moons at Saturn. Now, if you look closely at Saturn, you'll notice that there's a white ring around the planet. And this is where the sunlight is refracted through the top of the atmosphere into your eyes. And it's so beautiful because when you look at this ring around Saturn, you're seeing every sunrise and sunset on the planet at the very same time. And you're looking at the dark side of Saturn, and yet something is lighting up the night side. And what's lighting up the night side is actually light coming from Saturn's rings. So the sunlight hits the rings on one side, and it then reflects onto the night side of Saturn. So just one of the many, many incredible images that have come back from the Cassini mission. Now, I'm often asked, why do we explore space? Why do we send robotic emissaries out like Cassini? What are some of the grand questions we hope to answer? And Cassini addresses two of those. These are something that we're in a survey for planetary science. We do these once every 10 years. So the first grand question is, are we alone in the universe? Has life originated somewhere other than Earth, perhaps in our own solar system? And how did life originate on the Earth? Another grand question is, how did the solar system and the Earth within it come to be? How is it evolving, and where is it headed? By studying the planets in our solar system, we can learn about how our solar system formed, how the planets may have migrated as the system evolved, and where we might be headed. And it's a good analogy for other systems around other stars. Now and I just want to go back briefly here and show you, these are the 8 planets in our solar system. Saturn is the 6th planet out from the Sun. It's the 2nd largest planet, and it takes 30 years to circle the Sun a single time. Now, Saturn is indeed huge. It's the 2nd largest planet. This shows the Earth and the Moon to scale and the distance in between them. And so you can see that Saturn would just fit in between the Earth and the Moon. And if the Earth were a tiny marble, it would take 764 Earths to fill up the volume of Saturn. So truly a giant planet. And what you're seeing are just cloud tops. Saturn doesn't have a solid surface like the Earth. It's all clouds, mostly hydrogen and helium, and maybe a tiny rocky core about the size of the Earth in the center. Now here's an overview of the Cassini mission. Cassini was launched from the Earth in 1997. We used gravity assist, 2 of Venus, 1 flyby of the Earth, 1 of Jupiter, and arriving at Saturn in July of 2004. Now, originally, Cassini was funded for a 4-year prime mission. And by the end of the prime mission, we found we had enough fuel and a healthy spacecraft that we actually had 2 extended missions. The Equinox mission, where the sun was shining right on Saturn's equator, edge onto the rings, and then a 7-year solstice mission. And northern summer solstice at Saturn will be in May of 2017, and the mission will last just past that, ending in September of 2017. And you can see there at the end in the green box what we could call the proximal orbits or grand finale orbits, and they're shown above, highlighted in this box. And this whole mission is shown against the 30-year orbital period for Saturn. So by the end of the Cassini mission, at the end of 13 years, we'll have been in orbit in the Saturn system for almost 2 seasons. They change very, very slowly at Saturn. And right now, Cassini is almost to that green box. We're going up an inclination, and we're getting ready for our final set of orbits. This is another view of the Cassini mission by year. You can look across the top bar, shows the number of orbits and the shapes of those orbits. Then you can see that by the end of the mission, we'll have 127 flybys of the giant moon Titan. And Titan is like a giant rocket engine. Every time we fly by Titan, it's like expending almost as much fuel as we spent to go into orbit for Saturn orbit insertion. And we get great views of this very interesting body as well. We've had 23 flybys of Enceladus, and in the prime mission, the first 4 years, we had 3. We discovered Enceladus was so interesting that it reshaped our thinking for the extended mission, and we added 20 more flybys of Enceladus. We have 15 flybys of the other icy satellites, and then you can see the seasons changing from northern winter to northern summer over the course of the Cassini mission. And then, of course, those proximal or grand finale orbits at the end, and Earl will be talking about those in more detail. This is a Cassini orbiter and the Huygens probe. You can see a great model, a quarter-scale model over in the corner of the Cassini spacecraft. Cassini, she's about 22 feet tall. That antenna at the top is about 13 feet in diameter. It's comparable to the Voyager antenna you can see over in this other spacecraft here. You can see people for reference. And fully fueled, Cassini weighed 6 tons, and about half of that was fuel that we spent about a third of that just to go into orbit around Saturn. The Huygens probe was provided by the European Space Agency, and it was specifically designed with the goal of being thrust into Saturn and Titan's atmosphere, parachuting down and landing on the surface of Titan. Now, Cassini isn't just a spacecraft that's made up of metal and bolts and bits and pieces, but this is kind of my view of Cassini. I see Cassini as made up of all the people that are on her team, the scientists, the engineers, the support staff, and in a way, Cassini represents all of their hopes and dreams, all of the things that we want to accomplish. And there are times when I almost picture myself there with Cassini in the Saturn system as we get back some of these wonderful images or spectra or data of these incredible places. And I almost feel like I'm right there looking through Cassini's eyes and watching as she collects her data, and feel very proud to be a part of this incredible mission. Now on to some of the science. This is the tiny moon Enceladus. Enceladus is only 300 miles across. Enceladus would fit between Los Angeles and San Francisco, so it's a very tiny moon, and yet a very interesting one. When we saw it with Voyager, we saw a very bright, icy surface. Generally in the solar system, something bright means that it's young. You haven't had a chance to build up the pollution from the micrometeoroid bombardment. And also you'll notice as you go south, there are very few craters. In fact, there are no craters at the south pole of Enceladus. And you can see 4 tiger stripe fractures. That's our nickname for those bluish features there. Alexandria, Baghdad, Cairo, and Damascus. So have very interesting names, and those fractures were something that were in darkness when the Voyager spacecraft flew through the Saturn system. So we didn't know they were there until we had the Cassini spacecraft. Now, our first flyby in July of 2005, our magnetometer team said there's something interesting going on with Enceladus. The magnetic field lines from Saturn don't go down to the icy surface like they normally would for a body frozen solid. Instead, it kind of reminds us of a comet. Those field lines are standing off. There's something going on in the southern hemisphere. And so they encouraged us. We had a 1,000-kilometer flyby the first time. They said, go closer. We can really get a lot better data. So we went closer and also trained our other instruments on Enceladus. And we found here, this is with the composite infrared spectrometer, the team that I work with. They found that the Enceladus south pole was hot. It was about 100 degrees hotter than the rest of Enceladus. And if Enceladus were frozen solid, it was much hotter than it should be. And in looking more closely, that heat lined up with those tiger stripe-like fractures. So this excess heat was a puzzle. We had an occultation of a star going behind this region. We looked at these tiger stripes in more detail on the various flybys. Here's a tiger stripe. It's about a mile or so across, typically about 100 miles wide. And it's just this large gash, 4 of them in the South Pole. You can almost see what looks like a frosted side on the left-hand side there. We wondered what could be going on with these tiger stripes. We also had images, and the answer, it was very clear. There are jets of material, water vapor, water ice particles shooting out of these tiger stripe-like fractures. Here's another view of those jets coming out, just going all different directions, continuously going off ever since Cassini arrived at Saturn, and we've been watching Enceladus. So not only do you get water vapor and water ice coming out, you have things like ammonia, methane, carbon dioxide. You have many of the key ingredients that you might need to find life coming out of these jets on Enceladus. And part of the goal of our flybys is actually to fly through this material. And in October, we came within 50 kilometers of Enceladus' surface, right under the South Pole. And it gave us a chance to essentially taste and smell those particles, figure out what they were made of, and try and figure out the activity inside of Enceladus. Here's another view of those icy jets. This is a backlit view, similar to what you saw earlier in the Saturn image. You can see the sunlight shining through each of these jets. And we found in the particles that some of those were salty. There's a global ocean underneath Enceladus' icy crust, and it's as though there were frozen sea spray. And they contain sodium and potassium salts. And we know the pH of the ocean, very similar to the oceans here on the Earth. So very interesting finding in the particle data. This is an interesting view. This is another Enceladus. This is a fountain at Versailles in their gardens there. And this particular Enceladus is a Greek giant, and he had a run-in with his grandniece Athena, and he lost, and so his fate was to be forever buried under Mount Etna. So I think here he's protesting a bit with this giant 82-foot-high geyser of water. Who knew in the 1670s that Enceladus would actually kind of be doing something like this? Now here's an artist's concept of what might be going on. You have the liquid water ocean underneath the icy crust, and that carbon dioxide might be sort of like shaking up a champagne bottle. You pop the cork, and perhaps that's the energy that's there to raise that water vapor and icy particles to send them continuously into space. Now most of the material falls back onto the surface of Enceladus. The particles are too large, and they fall back, and it's like it's snowing. If you could stand near a tiger stripe underneath it, you could put out your hands and it would be like it would be snowing on Enceladus. Maybe a future vacation destination, who knows. But some of the tiniest grains escape into space. And they're what go on to form that very beautiful blue E-ring that you saw in the first image. If you look carefully in this image, you can see this tiny black dot. That's Enceladus. Underneath it is the bright plume of material coming out. And you can see wisps and tendrils of those icy particles going out to form the E-ring. Now the E-ring particles are so tiny that they spread throughout the system, and if you turned off Enceladus's jets, it might only take 100 or 200 years until the E-ring is gone completely. So that's sort of a clue. We see the E-ring, we know the jets are going off at Enceladus. This is just an artist's concept of the inside of Enceladus. We know it's differentiated. That just means it's separated into a rocky core, a global ocean, and an icy crust. We've also found that in looking at some of our particle data, there are tiny grains of silica. We call these nanosilica grains. What's unique about them is these nanosilica grains can only form in water that's near boiling. So what we think happens is that the water goes into the rocky core of Enceladus. It's heated up there. Enceladus is kept warm by a resonance with another moon, Dione, that's essentially just pumping heat energy into it. And once that water is heated up, it absorbs these minerals, in particular silica. When the silica comes back out through these hydrothermal vents, hits the cold water, those minerals condense into tiny particles. Then those particles are frozen into the particles that go out into space that Cassini can measure. So this is an indication that there's a possibility of hydrothermal vents on the seafloor of Enceladus. Now, if we look at our own planet, we have the same kind of hydrothermal vents on the seafloor of the Earth. This is along the mid-oceanic ridge in the Atlantic Ocean. It's very, very deep. No sunlight penetrates to that depth. This is illuminated from basically the headlight of the submarine that's looking at this particular event. And here you have silica and potassium and other minerals that condense in the cold water on the Earth's seafloor, forming what looks like smoke. And these are what is known as white smokers on the Earth. There's also something along the sea, depending on the composition, there are black smokers as well, and they're more iron-rich, so a different composition. What's interesting is here in the deep, cold ocean, where you have no sunlight, the only heat energy and nutrients are what's coming out of these vents. You find an amazing array of life. You find tiny crabs, you find tube worms, you find little tiny animals, all sorts of life in an island around these hydrothermal vents. And so we wonder if we can find life in our own ocean. Perhaps might there be life in the ocean of Enceladus. So some of the factors that life might exist there include a global salty ocean, pH very similar to our own. We know it's long-lived. A global ocean probably formed at the same time as Enceladus. There's organics coming from the ocean to the limits of the instruments we have to detect them. Carbon chains up to C6, C7. They're probably even longer, but that's the cutoff of the instruments, what we can measure. Heat energy coming from the hydrothermal vents on the seafloor. And best of all, for Enceladus, it's giving us free samples. And it turns out when we launched Cassini, we had no idea that there'd be these jets or vents coming out of Enceladus. So we didn't carry the instruments that we would have needed to look for amino acids and fatty acids and long-chain molecules that could tell us that life is there. So this just means that this is a wonderful destination, this ocean world, to go back to Enceladus and to keep exploring and answer the question, are we alone in the universe, or perhaps might there be life in Enceladus's ocean? Now, another very interesting moon is Saturn's moon Titan. Titan is about 10 times bigger than Enceladus. In fact, Titan is about the size of the planet Mercury. If Titan had formed anywhere else in the solar system, Titan would be a planet instead of a moon. Now, this was the Voyager view of Titan, and we just saw this hazy world, and we couldn't see through to the surface. So after the Voyager flybys in the 1980s, a group of scientists got together and said, you know, we really need to start thinking about going back. And it was both US and European scientists, and that was basically the birth of the idea for what became the Cassini mission. Now, Titan has a very dense atmosphere. It's made mostly of nitrogen, very similar to the Earth's atmosphere. No oxygen, but it has methane in its atmosphere. And methane is really the key at Titan, because you see, methane plays the role at Titan that water plays here on the Earth. The methane can be a gas, it can be a liquid, it can form clouds, it can rain onto the surface of Titan, that the temperature of Titan's surface is just right to be at the triple point where you could have a liquid, a solid, or a gas for methane. Now, the methane is also part of the problem with the smog on Titan, because you see some of the methane goes high up in the atmosphere. The solar photons, the UV, breaks the methane apart. They grow into larger and larger chains of molecules, and that forms haze, very similar to the smog that we have here on the Earth. When the particles grow large enough, they actually fall down onto the surface of Titan. Now, the Huygens probe was built specifically to go through the atmosphere, land on the surface, and reveal the surface for the first time. And so this is an artist concept of the Huygens probe. You can see it coming in. It was released from Cassini on December 25th, 2004, and entered into the atmosphere and landed on Titan on January 15th of 2005. So the heat shield basically ablated away, carrying away the heat energy. And once the probe had slowed down enough, then the parachute could come out. And for the next 2.5 hours, the Huygens probe floated gently down to the surface of Titan, softly landed on the surface, and returned data for another half hour. And Cassini was the relay, so as the Huygens probe was floating down, Cassini was flying overhead, collecting the data, then to send back to the Earth for the Huygens probe. So really an amazing mission. With Huygens, we didn't know what we'd find. Would we land in an ocean, global ocean of methane? That was a possibility. So we built the Huygens probe to float, at least for a few minutes. But it turns out that we didn't have to worry about landing in an ocean. Instead, here's the view that we had with the cameras. We measured not only the pressure, temperature, and composition of Titan's atmosphere on the way down, but the cameras took these pictures. And about 60 kilometers above the surface, the haze finally started to clear, and we got a view of the surface. And we started to see what looked like mountains as we went on our way down. And in fact, the Huygens probe became the very first object to land in the outer solar system, land on a body the furthest away from anything we've had previously. Here's a view of the surface. You can see on the leftmost panel, these are rounded icy pebbles. It tells us that fluid has flowed in this region. Probably we landed in what was the equivalent of a dry lake bed. We had a lamp. You can see the spot for the lamp here to give us an idea of what the color might be of the surface. And you can see the icy pebbles here. And here's a really neat comparison. This is from our own moon. Here's a footprint of one of the Apollo astronauts. You can see the astronaut and the little flag up here. So this is sort of the same perspective view that we had on Titan. And we also could see all of these channels indicating that indeed methane was flowing. And we found a world that was remarkably like the Earth in so many ways. In fact, there were lakes and seas at Titan's North Pole, lakes of methane. In fact, this Lake Ligeia Mare is about 50% larger than Lake Superior. It's about 500 feet deep, which is about the depth of the Great Lakes as well. So there's a tremendous volume of methane on the surface of Titan. And in fact, if you could gather up all of that methane, knowing the depth of this sea is a typical depth, you'd have 10 times more hydrocarbons than all of the reservoirs we have here on the Earth. So if only we could build a pipeline big enough to go from Titan all the way back to the Earth, our problems would be solved. But there's just tremendous amount of hydrocarbons on the surface. And you can see the channels flowing into that particular sea. Dunes, those particles that form high in the atmosphere, fall down, form these long, dark, linear dunes that wrap around the equator of Titan. Those long, dark, linear features. There's also mountains. This is a mountain color-coded with height. Mountains can be as high as 1 kilometer or so on Titan. And we think perhaps in this case, you look at it, it might have even been an ancient cryovolcano. Perhaps water mixed with ammonia flowed out on the surface of Titan. And perhaps with that water, perhaps came the methane. There's not enough methane in Titan's atmosphere to have lasted from the time Titan formed. So there needs to be some internal source periodically releasing methane. Otherwise, once the methane gets divided up in the upper atmosphere, the atmosphere would collapse. So there's some source of that methane. Clouds, we've seen lots of clouds. This is a colorized cloud. We've seen lots of clouds and weather on Titan. We even saw a rainstorm, a methane rainstorm on Titan that darkened the surface, and then we watched with time as the surface slowly dried up. Then here's a view of the dry riverbeds. Now, in looking at these images, what you see here, the lakes and the dunes are taken at radar wavelengths. Radar wavelengths are very good at penetrating through the haze, and so we really have gotten tremendous views of a large portion of Titan's surface. This view is what you would see with the cameras. You can see hints of the lakes in the North Polar region. What we did is we carried near-infrared filters specifically designed to go through and penetrate the haze and look at those. One of the things in the beginning we didn't know for sure is, in those lakes, was that truly a liquid or some kind of a goo or something? What really was it? And we were trying to figure out, how do we find out if it's a liquid without going there, landing in the lake, and finding out? And it turns out we have another instrument, the Visual and Infrared Mapping Spectrometer, looking at near-infrared wavelengths, and at 5 microns it found a bright spot called a specular reflection. If you have sunlight coming at an angle reflecting off a liquid surface, it comes out at the same angle, and if Cassini is looking at that angle, you'll see a bright spot over the lake. If you've ever been on an airplane, sometimes if you're looking out the afternoon window as you go across a lake or a river, you might notice there's this bright spot that pops up when you go over a liquid, and that's a specular reflection. Now, I just want to say a little bit about the rings. The rings have very simple names, A through G. We keep naming them with other letters as more of the rings are discovered. The main rings of Saturn. Saturn is off to your left. The main rings that you would see through a telescope are the A ring. The Cassini division, which is the astronomer that discovered Cassini division and for which our mission is named. The B ring, which is the most optically thick ring. And then the C ring. And there are also additional rings just shown in the bottom panel. Here's the innermost D ring. It's very, very faint. You've got the tenuous, very narrow F ring just outside. Then here you have the E ring going all the way out to Titan. And it turns out there's one more ring in the Saturn system. And this ring wasn't discovered by Cassini, but it was discovered by ground-based observers, and it has created by Phoebe. So there's a ring, the Phoebe ring, that actually comes in to the Saturn system as well. Now here's a Cassini view of the rings of Saturn. They're made mostly of water ice, and on average they're only 30 feet thick. So incredibly narrow for the hundreds of thousands of kilometers that they span from end to end. There's tremendous amount of detailed structure there. Some of it we understand is the interactions with the tiny moons just outside. But so much of that structure, we still have no idea what's causing that incredible structure. We do know that there are 2 moons that actually orbit in the rings. There's one that orbits in the Encke gap, named Daphnis, another one named Pan. These 2 moons keep their gaps open. So we know that, that information about the rings. And here's a nice view of the very dark, very, very tenuous D ring. Now this is the lit side of the rings, what you would see through a telescope. But there's also another side to the rings. And this movie was taken by Cassini. Basically, you're riding along as Cassini is plunging down through the ring plane. You can see the A ring, Cassini division, and B ring. Every once in a while you'll see a tiny moon go by. There's Titan. You can see it's much larger. Now you get to see the other side, the dark side of the rings, the side where the sun isn't shining. In this case, the B ring blocks out all the sunlight. The Cassini division is very bright. The A ring is bright. And you can just see a hint of the bright C ring. So the rings look very different. And that's the advantage. If you go to a place like Saturn, you can see the rings on both their lit and their unlit sides. Now, Cassini also had a rare opportunity at equinox. In fact, we just had our autumn equinox, just I think very early this morning. And that's when the sun shines directly on the equator. And in this case, it shines on the rings edge on. And that's important because with the sun edge on to the rings, essentially you've turned the sunlight off for the rings. And this mosaic taken by Cassini, what we've had to do here is increase the brightness of the rings by about a factor of 20. So you could even see them because they're only now illuminated by Saturn shine. And around on the dark side of the rings, where it's dark and before Saturn's shadow, we've had to increase the contrast by about a factor of 60. Now here you can see the narrow F ring, but it's slightly tilted. So it can still catch the sunlight even around equinox. Now with 30-foot thick rings, what's unique is you can look for anything that sticks up above or below the ring. So if you're bigger than 30 feet in size, there's a chance you'll cast a shadow and we can see you. So we're looking for objects with Cassini that would be larger and would cast shadows. And so I'm just going to show you an image now. This is the outer edge of this ring, the B ring, and it's stretched out. And lo and behold, we found shadows, lots of them. Turns out that the outer edge of the B ring is held in place by a resonance with one of Saturn's moons. And it looks like some of the largest particles, or maybe they form and grow right there at the edge of the B ring. Now some of these are probably a kilometer or two in size, casting very long shadows. But there are hundreds of them across the B ring, almost looking like little mountains along the B ring. And a good analogy is if you wanted to, say, find the pyramids, if you're looking out from the space station, if you looked around noon, they'd be hard to see against their sandy background. But if you looked near dawn or dusk, the equivalent of equinox, they would cast long shadows, making them much easier to pick out against the sandy background. So in the same way, Cassini used this to look for structures, and we found a number of different structures like this that would cast shadows in the ring. So as a ring scientist, a very exciting time to be looking at Saturn's rings. And finally, here's a very interesting discovery for the rings. It turns out that there is a feature. This feature is about 1,200 kilometers long, 10 kilometers or so wide, indicating that there's a tiny object 2 or 3 kilometers in size creating this feature. This feature is right at the edge of the A ring. So it was discovered in 2013. Its discoverer, Carl Murray, discovered it on his mother-in-law's birthday, so he nicknamed it Peggy after her. So this tiny object that's here creating this feature, Peggy, we've been watching for her ever since. She comes and goes. We're wondering, will she break free of the rings and become a moon in her own right? Or will she be torn apart and jostled by the other particles in the rings and disappear? So far she's still there. We're going to keep watching for her through the end of the Cassini mission. We're kind of rooting for her by now because she's been around for a few years. Moving on to Saturn, one very interesting event happened at Saturn. A giant storm developed toward the end of 2010. This storm grew so huge, it was a giant vortex, and that vortex swirled off this huge tail. The tail of the storm wrapped itself around the planet. There was another vortex on the other end, kind of like a hurricane. When these two vortices merged, that marked the end of the storm. A tremendous amount of energy was released in this storm at Saturn, and typically these storms happen about once every 30 years. And so this was the 5th time we've seen a giant storm like this at Saturn. But what was unique is this storm was early. It had only been 20 years since the last storm, and so it came early so Cassini could get a good view of it and watch it. And so we watched it, as did ground-based observers. It lasted about 9 months and started to fade. Now this is in the visible. If you look toward the near infrared, you see deeper into the atmosphere. The colors in this view, if it's white or yellow, that's high up in the atmosphere. Green is also high up. That's the center of the storm. And then the oranges and the reds are looking deeper. So we're basically getting a profile of what that storm looked like and how those clouds behaved. And we can model that and perhaps use it as an analogy to storms in the Earth's atmosphere. Now looking at some of the longest infrared wavelengths, the thermal infrared, turns out that the storm was in the lower atmosphere of Saturn, the troposphere. But when those two spots merged, it released a tremendous amount of energy, kind of like a giant burp. And here up in the stratosphere is a large, very hot feature. And this feature persisted for a couple of years and has slowly cooled. So a very dynamic and active Saturn. at least in that time period. Now, Saturn has a very interesting feature at its north pole. Here's that feature. You're looking right down at the north pole of Saturn. That feature is a six-sided jet stream called the hexagon. The Voyager spacecraft first saw this feature in the 1980s, and it was still here when Cassini arrived. You can see the pinkish clouds. This is a false color view rotating around, and they go faster the closer you get directly to the North Pole. And at the North Pole, there's a giant hurricane. And this hurricane is about 50 times larger than a typical Earth hurricane, blowing about 340 miles an hour. And finally, before I pass it over to Earl, this is a view of the changing seasons. In fact, Saturn's shadow on the rings you can think of as a giant sundial. And this picture taken back in April of 2016, you can see that the shadow of Saturn goes out just past the Cassini division. At solstice, that shadow will pull in until it's about in the middle of the B ring. And so as that shadow pulls in, so will Cassini's time shorten at Saturn. With that, I'd like to turn it over to Earl to talk about the grand finale.
So how does Cassini follow that? How do I follow that? I want to go first next time. You know, one of the things about Cassini is it always trumps itself. You know, as we keep finding, you know, one year we announce a subsurface ocean, next year we announce a global ocean. So it keeps building and building and building. And then you look at the last 12 years, and how do we do something even more spectacular in our final year? Well, I'm going to show you at least the potential for that. But before we do that, I want to do just a little bit of a backup here. I want to go to the end. This is September 14th, 2017. It's about 2 o'clock in the afternoon here in Pasadena. And Cassini has just wrapped up a 30-hour or so observing session. The recorders are packed full of images and data, fields and particles data. And so now it's time for Cassini to turn back to Earth and begin to play those back. So this is a high-speed, slow-speed version of the last of these periods. So Cassini's going to be working on this for about 10 hours. The DSN is going to be receiving all this data. We are going to be streaming these back, and as soon as we see them, you'll see them. Some spectacular images of the poles and of the rings as we come in. And then when the SSRs, the solid-state recorders, are empty, it'll be about 10 hours. Cassini's going to reconfigure for the periapsis here at Saturn. I want to make sure So we've done that 292 times over the last 7 years. Periapsis at Saturn is pretty routine, but not this one. This one is absolutely unique because it's Cassini's last. 3 days before this event, Cassini had a close encounter with Titan. Titan gave it a little gravitational nudge, and that nudge has pretty much sealed Cassini's fate. As a matter of fact, it's not coming out of this periapsis. It's moved the periapsis, the closest approach distance, inside the capture radius of the Saturn's atmosphere. And so Cassini, this one, is going to reconfigure itself so that it doesn't put the data on the recorders. It's going to put everything out on the pipe as quick as it can. So the minute you see, now it's going to start to turn colors here as Cassini reconfigures. Cassini's going to go into the atmosphere, and every second of this data is going to be coming back to the Earth. And unfortunately, Cassini is going to be going 77,000 miles per hour. You can get around the Earth in about 20 minutes at that speed. So what's going to happen? It's going to happen very, very fast. We are going to have every piece of data streaming back down. We're going to be sampling the atmosphere and trying to answer some of the fundamental questions about Saturn's atmosphere. But it's not going to be very fast, not going to be very long. At 77,000 miles per hour, Cassini is going to be going in with its antenna pointing to the Earth, but the atmosphere is going to quickly overpower its ability to point. It just doesn't have that kind of control. It's going to push it off, and then we'll lose comm. It will essentially disappear from our monitors, and about 3 or 4 minutes later, that speed and the density of Saturn's atmosphere will vaporize Cassini, and it is over. One of the most spectacular missions ever to leave Earth, a discovery machine like you will never see, and it's going to be done. So Why are you doing that? I mean, the first thing, did you guys ask anybody's permission to take something that is rewritten, science programs, redirected NASA programs, and recontoured missions? You're just going to destroy it? Let me give you I'll try to explain why we think that's a good idea. In order to do that, I got to go back a little ways. So back to 2009. Linda told you about the prime mission and the extended missions. We got to Saturn in 2004, right? We had a 4-year mission, but we didn't have any end. There was no end game planned. But we got to the end of that mission, realized we had an incredibly good spacecraft, lots of propellant, so we went for another 2 years. About midway through that second mission, 2009, we said, geez, all subsystems are great. This system is wonderful. We've got a lot of gas in the tank. Let's do something else. So what? What's next? And we actually got a lot of studies done. You know, there's a lot of opportunities at this point with all the subsystems going. We could have left Saturn. We could have gone off to the Centaur asteroids and turned ourselves into, repurposed Cassini as an asteroid mission. We could have, believe it or not, left Saturn and gone to Jupiter, or gone out to Uranus, or gone out to Neptune. Now, I got to say, this was a 40-year cruise, so, you know, I mean, it would have been a long cruise, but, you know, look where Voyager is. It was possible. We could have gone back to Jupiter. That actually is an image we took on our way out, and we could have gone back and spent, you know, the same set of resources on Jupiter as we did on Saturn. Uranus is also a possibility, or more of Saturn. Well, you know, this is kind of a no-brainer. I mean, we had barely scratched the surface. Saturn is just incredible. You couldn't have asked for a more dynamic environment. You've got the rings, you've got the planet, you've got the icy satellites, you've got Titan and Enceladus, little prebiotic worlds on their own. And Cassini's still unwrapping this. So it's really not hard to figure, okay, we got to stay. So, you know, I'll jump to the chase real quick. Nah, we're not going there. Nah, we're not going there. We're going to stay. But there's a catch. If you want to stay at Saturn, there's some rules. And they are, we call it planetary protection, but the real essence of this is you've got to protect Saturn's ocean worlds. Cassini is essentially a victim of her own discoveries. My apologies to the Oak Ridge boys, but you can visit, but you can't stay. So you've got to make sure that if you stay in the Saturn system, there is no possibility of a crash landing on Enceladus or Titan. Cassini is room temperature inside. If there are little microbes in there that don't mind a vacuum, they could last forever. We were running essentially at about 72 degrees inside the spacecraft, and so going and taking some of our Earth microbes or spores onto Enceladus in particular, where we know there's water, warm water, would just be absolutely unacceptable. So you guys can stay, but you got to be careful about what you do about Titan and Enceladus. So with that in mind, you say, well, how are we going to do that? We could stay and do big long orbits, you know, stay way outside the orbits of Enceladus, way outside the orbits of Titan, but guess where all the science is? It's down there with Titan and Enceladus. So we want to explore these guys, but we want at the same time remain safe. So we go to the trajectory designers. We got a fair bit of propellant. We got good subsystems. What can you guys do for us? We want to be able to stay inside Saturn's system. We want to explore all the icy satellites. We want to explore the rings of Saturn, but we want to still remain safe for these two, you know, incredible worlds. So what these guys gave us was the Solstice mission trajectory. This started in 2010, and this is a trajectory designer's masterpiece. It's a lot of squiggly lines, but each of those is an orbit, and every time that orbit changes shape, it's because Titan moved us. As Linda said, we get essentially a Saturn orbit insertion velocity change every time we fly by Titan. So you want to go up, you fly under Titan, and it pulls you up. You want to go in, you go to the right, go to the left. And we take you all over the system. So what we did, what the trajectory designers did, they took these orbits, we stayed very flat in Saturn's plane. That's, by the way, that's Saturn there in the middle. Very flat, and then you could stay and do all the satellite interrogation you want. You could go very inclined, very looping orbits to do magnetic fields and to do the poles and the rings. And as a bonus to all of that, this is the first 6 years of this mission, the mission that Linda just reported. You also get this. This is the last year of the mission. And this is, unfortunately, at the end, the demise of Cassini, as I described just a few moments ago. But on the way in, we have an entirely new mission, something we have never done before. We're going to flirt with the outsides of the rings, and then we're going to go diving deep in between Saturn and the rings. And I'll show you a little bit more about that just to show off some here, because these things are just phenomenal. The key orbital characteristics of this final set of orbits, which we call the F-ring and proximals, you'll hear some of the flight team call them FERPO, which sounds more like a dog food than a real acronym, but really they're the F-ring orbits and what we're now calling the grand finale. 42 short period orbits. Each of these orbits lasts about a week. The flight team is going to be running around like you've never seen. 20 of them are going to be, oops, I've hit the wrong button, sorry. I hit it again. There we go. 20 of them are going to be just outside the F-ring, right? This is the outermost ring here. Titan is going to be, and both of these essentially run into Titan right out here. 20 of these outside with great coverage of the poles and the rings, and then another Titan flyby is going to move us in to the gap between the innermost D-ring and the outermost edges of Saturn's atmosphere. 22 of those. The periapsis is going to be in what we call the 2,400 kilometer clear zone between essentially Scylla and Charybdis. We've got the dust on the left and we've got the Saturn on the right. We've got to navigate in between. Next slide is, I think, a look at the view from Earth. Not only are these things phenomenal from their proximity to the system, the geometry is also phenomenal, because if you look at what happens here, these orbits go behind the rings and behind Saturn. Almost every one of them, from a view from Earth, provides what we call occultation. Not only do we have instruments that can photograph and sample, we also have instruments that can send a very, very precisely tuned radio signal to Earth. And passing that signal through the rings and the atmosphere can tell us a tremendous amount about their internal structure. The opportunities here are absolutely phenomenal. And we, by the way, Saturn is obliged by never, if you recall back to Linda's picture, never opening up the rings more than they are right now. So essentially be passing these waves right through. It's an absolutely unique and spectacular opportunity. This again is just to show a little bit of what happens at the periapses. You can see, you don't quite see the F-ring on this illustration, but it is right. Oops, I've done it again. Here we go. We have these rings here. The F-ring is actually coming out right here. We have about an 8,000 kilometer gap there, but there's extended dust. And if you look at the F-ring, I'm actually more terrified about that than I am about the gap, because of these tendrils that keep coming off the F-ring. But nevertheless, that's where we're going. And then, again, you see the proximity of these periapses here inside for what we call the proximals, the grand finale. This is, again, just kind of showing off, but here is a flattened out version. These are the rings of Saturn. Here's the F-ring up here, and here is Saturn's atmosphere down here. Atmosphere. Saturn doesn't have a surface, or if it does, it's way down in there. So what we call the surface is essentially the one bar level, essentially the pressure at sea level. So that's what we're calling the surface of Saturn. So here are graphically each of our periapses. So we're flirting around in this safe little gap between the F-ring dust. I've done it again. We'll get to that. Between the rings here, incredibly precise navigation to stay between the dust hazards, between the F-ring and the Janus and Epimetheus rings here. Then the Titan flyby that brings us down in here, and then we stay very carefully and very precisely within the gap between Saturn's atmosphere and the dust until our final flyby here. Now, I should point out there are a couple that are actually flirting with this, and we're going to do some things here to keep ourselves safe, because they're a little bit more dicey than the others. Okay, so what's it like to be on Cassini when we're doing this? I've Already stolen my thunder on this slide a couple of times. Imagine you're just sitting on the prow of Cassini going through. This is 7 seconds of terror every 7 days for 7 plus 2 months. So Mars has got their 7 minutes. We got 7 seconds every 7 weeks. And this is the white knuckle time for us. Now, we won't know because most of the time going through here, we don't want to have the spacecraft talking to us. We want it to be doing science. So we'll find out if we've survived these ring plane crossings much later in the game. But that's the way it goes. You want to get the science. You don't want to find out if you're going to make it. So this is going to happen 22 times every Tuesday, I believe. But I could be wrong about that. And so the flight team, there are many of them here, we are going to be very, very busy. So the science. I love the engineering of all of this, but really the engineering is all in it because of the science. And this is just some of the unique things. You've seen what Linda showed already, and it is phenomenal. And we're going to continue to do some more of that even while we're here. But these are opportunities that we will never, ever get any other time. Saturn internal structure, magnetic fields, and gravity. We'll actually be able to determine for the first time the mass of the rings. By flying in between the rings in Saturn, we can get a sense of where which one's which. And that tells us something very fundamental. Believe it or not, we don't know how old the rings are. They could be a couple 100 million years, they could be 1 billion years. There's a big argument about that, and very, very intelligent people on both sides of the case. We think we can help with some of these measurements. Saturn's atmosphere and the innermost ring particles, and the highest resolution ever ring observations themselves. When we went into orbit in 2004, we went over the rings, but they were not lit. We got the dark side. So now we can finally see these rings fully illuminated by the sun. And as I showed that picture earlier, Saturn's cooperating by providing an incredibly good phase angle with the sun. And also, we're going to radar the rings. You saw the radar images of Titan. We're going to try to do the same thing with rings. Polar observations and aurora of Saturn. And then finally, as I mentioned in my first slide, we are actually going to sample Saturn's atmosphere. Every ounce of Cassini's last efforts will be made in sampling the atmosphere and trying to understand and answer some of the fundamental issues about the constituents of the hydrogen-helium ratios and things like that. So we'll see. Let me just quickly run through this. November 30th, right after Thanksgiving, this whole thing starts. And this is just to show you that not only sometimes you're good and sometimes you're lucky. The longitudinal coverage of the F rings is absolutely phenomenal. We're going to get the whole planet covered with the F ring timeline, 20 orbits. April 22nd is our first targeted flyby. This was last targeted flyby, and this is the one from Titan that's going to push us in. So I'm going to try to not hit the go button and show you. Titan's going to come in from over here. Here's the F ring, final F ring orbit. We're going to come out back around, and then here comes Titan, and watch what happens to this orbit. Boom. It does. It's about a couple of thousand kilometers, so it's pretty close. But now, rather than going outside, in we go. And that's going to happen for 22 times. Boom. And so there's that, and I won't show you 22 more. April 23rd, the grand finale begins, and we have a lot of Titan flybys pushing us around. I won't show you a whole lot of those. But the first dive through the gap, and here's our longitudinal coverage with the proximals. Again, it's almost a perfect grid all the way around the planet. Absolutely phenomenal. First dive through the gap was on April 26th, and then September 11th, our last flyby of Titan. And I mentioned that before. We call it T292. It's a distant flyby, about 100,000 kilometers, but it doesn't take much to push us in to an impacting trajectory. And September 15, boom, we're in. The end of mission and the end of a very spectacular set of investigations at Saturn. So I want to share a cartoon with you that we at the flight team like to pass around. Hey, Cassini, I hear you're retiring. How about that? Congrats. Do you want to celebrate? Maybe lunch with me and my moons. How about that? Nah, I'm just going to go barreling straight into your atmosphere. learning as much as I can before I'm crushed to death and vaporized in a spectacular whirling inferno beneath your mysterious stormy clouds. So you can imagine Saturn's reaction to that. It's the same. It's the same one that we all have. Maybe you all have when you see that we're going to burn this thing up. You think about that for a little bit, and hopefully what I just told you might come to agree with all of us that it's too bad. It was a wonderful machine. It's been an incredible discovery machine, but it's awesome. But, okay, I think we'll be happy to entertain any questions you might have. And if you do have a question, we appreciate you going up to the microphone.
Thank you for a really awesome presentation. So I believe that the Juno mission is using highly elliptical orbits to explore the internal structure of Jupiter. And I assume you mentioned that you're going to be probing the magnetic and gravitational fields of Saturn. So my question is, at Jupiter, they expect to confirm the existence of metallic hydrogen inside of Jupiter. Is Saturn have enough gravitational pressure to form metallic hydrogen, do you believe?
Yes, Saturn certainly has enough pressure inside to form metallic hydrogen. We're wondering if we can maybe also detect that boundary inside of Saturn. Just want to point out one difference between Juno and Cassini. Juno is in a polar orbit, basically going over the poles. Cassini, we're only tipped at 63 degrees. And that's basically our optimum orbit to keep the periaps from precessing and putting us prematurely into the ring. So very similar complementary science for the two missions, probing the interiors of two gas giants and then comparing the results.
Thank you.
Thank you for the great presentation. I wanted to ask about contingencies during this final year. You're on a risky pathway, and if something were to happen to the spacecraft on one of these passes through the rings, what do you expect to become of the rest of the mission? Is there a chance that it can still have its crash into Saturn, or what?
Yeah. One of the things that's pretty amazing about this trajectory is once we've flown by that final Titan flyby, if we lose the spacecraft, it's still going in. And as a matter of fact, after T125, we require, which is the penultimate Titan flyby, and very minimal trajectory maintenance. We're essentially on a ballistic trajectory to our entry. Now, that being said, we're still going to try to. We've worked contingencies in case we find the dust is higher than we want. We can hide behind the high gain antenna. If the atmosphere is thicker than we would like, although some of the scientists think that's just great, we can move ourselves out a little bit. So we have worked a lot of contingency plans to make sure the mission is as successful as possible. But if we are damaged, we'll be able to keep our promise to Enceladus and Titan.
In fact, if the atmosphere shrinks, and that's a possibility, we also have a plan. We could go a little bit lower because we want to dip our toe for sure in that atmosphere of Saturn.
Hi. This is more of a question about the capability of the spacecraft. So I understand that the decision to deorbit it is quite final. But would it ever have been possible to attempt is there sufficient delta V in the tanks to attempt a rocky or icy moon, like smaller moon landing, like a janky near style, landing, and use the low gain antenna, send another spacecraft later, and have a passive station sitting in orbit around Saturn?
No,
would there be any value?
I'm afraid, well, that could have been, in that set of scenarios, there may have been a landing scenario that we didn't work, but now there absolutely is not. When we designed the Solstice mission, we designed it, you don't want to end a mission with a full tank. In fact, you want to end the mission with a completely empty tank, and right now we are almost completely empty. So the possibility of a controlled landing on anything would be absolutely out of the question. Again, those sort of things, most of the controlled landings that we see are really more like controlled crashes. They're low-speed crashes, and so really the realistic opportunity to create a beacon, I think you want to design something like Huygens that actually was built to broadcast up, but unfortunately it was on batteries, and that was that. But now it's, like you said, the decision's made, and we have spent all our propellant doing what we've been doing. Thanks for the question.
Thank you both for that presentation. It's excellent. You noted earlier you're concerned over contaminating the environments of Enceladus and Titan. How were you able to prevent that when you landed Huygens probe on the surface of Titan?
Good question.
Excellent question.
I think the key difference between those is that Cassini is powered by these radioisotope thermoelectric generators with plutonium on board. And so to access the ocean on Enceladus, you'd probably have to melt through some ice. And with the heat from that plutonium, that might be a possibility. The Huygens probe had batteries and it had some small RHU heaters. And also, when we landed on Titan, we didn't know about the methane lakes. We didn't know that Titan also had a global ocean. We didn't know about Enceladus. So a lot of things, like as Earl said, Cassini is kind of a victim of her own discoveries.
I see. Thank you.
Well, absolutely superb presentations, of course. A quick question. What's the cause of the highlights that we see here at 12 o'clock and 6 o'clock on the outermost rings?
Excellent question. What is the cause of those bright spots? It turns out that those spots are actually, you can think of, somewhat pulled in closer to the sun, and so it's sort of a phase angle effect. If you can think of it that way, the ANSA are further away from the sun than the points at the north and the south, and so they are brighter. As many things brighten as you get toward that very low phase angle where that distance between the sun and your target is small. Good question, though. Good catch.
To start, thank you for a wonderful presentation. I've really enjoyed it. Knowing what we know now about Saturn, what's next, and when do we get to go?
It's yours.
Well, there's a proposal cycle underway now within NASA called New Frontiers. And there's a fixed list of missions for New Frontiers. One of those is a Saturn probe. Much as we had a probe into Galileo's atmosphere, we'd like to send a probe into Saturn's atmosphere, in particular to measure the Nobel gases that you can't really measure any other way. And there are a host of other things you could do with the probe. There are also now 2 targets that were added to the list for New Frontiers. Those targets are Enceladus and Titan, basically these new ocean worlds unveiled by Cassini. And so there are missions to go to fly through the plumes of Enceladus with more capable instruments to perhaps look for those amino and fatty acids, missions to maybe land something in one of those seas on Titan and make measurements there. So there's a whole host of proposals. There's probably 30 or 40, or who knows how many NASA will get sometime next spring, and then they'll get to pick one of those missions. So we might go back as early, but it still is a long trip. You're talking about maybe a launch in the mid-2020s, 25, 26, and then maybe a decade or so to get back to Saturn. It's not a quick trip to get there.
I can't wait. Thank you.
And don't forget Uranus and Neptune. I mean, they're out there too, and it would be great to send a flagship mission like Cassini on out to one of the ice giants, Uranus or Neptune. We've just had tantalizing glimpses with Voyager, and to go back to one of those places for a future flagship, maybe after Europa, maybe a flagship to Uranus or Neptune.
Thank you so much.
I'll jump in for one more question. How long does it take for an image to get from Cassini to Earth, like to get the data here? And my iPhone, I think, has 8 megapixels. What's Cassini have?
1 megapixel.
1.
And it's black and white.
Okay.
We colorize our images with filters. And it takes anywhere from an hour to 90 minutes for the image to get from Cassini here to the Earth.
The whole megapixel image to...
Well, the megapixel, let's see. We do 140 kilobits per second. Okay. So it takes 10 seconds or so, roughly. Let's say 20, counting overhead, to get an image down here once it starts. But Saturn is an hour and a half light time away. So when Cassini starts to send a signal, her bits don't get to the ground for an hour and a half
For an
later.
hour and a half.
Yeah.
Gotcha.
And so when we want to signal, send something to Cassini and have it answer, we have to wait anywhere from 2 to 3 hours. Yeah.
Wow. That was really great. Thank you.
It just means Cassini has to be very smart. She has to basically have commands on board to keep her going, typically for 10 weeks at a time. Where to point, where to look, when to send data back. And so very, very smart spacecraft.
Actually, speaking of photos, I was wondering what the plan for in the grand finale photo was like, and what are you expecting to see? If you're expecting to take photos, are you expecting to see maybe some resolving some individual clumps of ice in the rings since you're going so close, or looking at the clouds of Saturn because the periapsis is going to be so close? Are you guys expecting to take a lot of photos from this mission?
Well, we're taking a lot of photos of both the rings and the planet. Ring particles on average are millimeters to centimeters in size. Even if they were tens of meters, we still couldn't resolve an individual ring particle. But we certainly could resolve the structure that we see in the rings at much higher resolution. SOI, as Earl said, is on the dark side of the rings. This is a chance to look at that resolution, but on the lighted side of the rings. Radar of the rings as well. Also, we'll get close-up views of the planet, of the poles, of the atmosphere itself. I think that the surprises might be the questions we don't yet know to ask. When we look at those pictures, whether it's the rings or the planet, what might we see? Also, we have a detector that some of those tiny ring particles from the main rings charge up, and the field lines then will go into one of our sensors, the cosmic dust analyzer, and we'll get for the first time the direct composition of the rings. We know they're water ice, but we don't know if the non-icy component is silicates, iron, tholins. We don't know what it is. So we'll get the answers for that for sure for the first time.
I might also add that as we enter the atmosphere, everything is going to be focused on atmospheric construction and constituents. The spectrometers, the fields and particles, they'll be pointing at the atmosphere. Unfortunately, that means the camera is going to be pointing someplace else. And furthermore, in order to play all that data back as fast as we can, we've had to narrow down the bandwidth. And a megapixel is a megapixel. We could get 10 or 20 mass spectrometer packets down for one image. So the camera's not even going to be recorded and sent down during those final seconds.
Thank you.
You said in response to an earlier question that you're getting pictures in black and white and then you're coloring them with filters. How does that work? Are you choosing, or do you know what filter colors you use?
Our cameras have 2 filter wheels. Essentially, you can take a green, blue, and magenta filter, not magenta, blue, green, well, whatever the 3 colors you pick, and colorize them, right? It has infrared filters that penetrate the haze. And so each of these filter wheels, you actually rotate that filter into the image path and take an image, then rotate another filter, take another image, and they're combined and colorized on the ground.
So the colors you end up with represent what you're actually looking at, or is it?
They can, or they can represent some of the false colors that you've seen, like the red hurricanes and things like that, that accentuate levels of elevation or of chemical constituents.
Okay.
A lot of the pictures you've seen were natural, but some of the others were false colored to highlight whatever meteorological or chemical item you're trying to look at.
But you can get true color. You take those filters and add them together in different ways, and you get the true color that you would see with your eyes in those pictures.
Thank you.
Hi. Thank you for your presentations. I have 2 questions here I want to ask. First is that you guys said that the Cassini satellite, the Cassini drones, props, whatever, is the farthest from the solar system we has ever gone. Is it?
Oh no.
No. Well, what I said was that the Huygens probe landing on the surface of Titan is the furthest we've landed a probe on the surface. But the furthest spacecraft now away from the sun would be the Voyager spacecraft. They're well past the orbits of Neptune, Pluto. They're on out, even one of them into the interstellar wind. So
our 90-minute light time, they're a day and a half for a signal to get from the probe to Earth. So they're way out there.
I see. And the other question I have is that if I remember correctly, Saturn has 5 big moons, correct? And so why do you only land on two of those moons?
Well, Titan is the very biggest moon, and it's the only moon in our solar system with a thick atmosphere. And it was the one that had the most questions and puzzles about it. So we really had the weight on Cassini to carry just a single probe. And so it was easiest to land on Titan. You could land with a parachute. You didn't need rockets or anything fancy. And we wanted to see what that surface looked like. So if we go back, we could carry probes that could land on multiple moons and look at those as well.
Oh, okay. So you mean that you choose the moons you want to land before?
Right. We chose Titan. Before Cassini even launched, we had chosen Titan.
Oh, okay. I see. Thank you.
Thank you for the very amazing talk. I had a question on a radio occultation. For the 3 different frequency centers that you have available in the spacecraft, can you characterize a little bit on ring particles that are smaller than the shortest wavelength and larger than the longer wavelengths, and the diffraction patterns and how we would be able to ascertain the particle population?
Right. The 3 wavelengths of the radio science are very diagnostic in helping us understand the particle size distribution of the ring particles. And what we found in looking at those is they're pretty much seeing all of the particles that in that particular size range for that. So they do a good job, the Ka, X-band, and S-band, in looking through the rings. And sometimes the S-band signal is blocked out first because the rings are so optically thick.
And how does the diffraction or dispersion occur on particles that are outside those wavelength correlations?
Well, the radio science actually has a fairly large field of view, and so it's integrated particles all the way across that field of view. And sometimes we see diffraction patterns that tell us that the ring particles are lining up and are structured in a certain way, forming these things we call self-gravity wakes. We can actually do some work to detect those in radio science as well. If you want more detailed answers, I can give those if you want to come up afterwards.
Thank you.
So this is more of an engineering than a science question, but for all these precise orbital maneuvers, how do you know your position accurately enough to perform these maneuvers?
Ooh, that's a good one.
Because you can't exactly open Google Maps and get your GPS, right?
I got to brag a little bit because JPL is the absolute center of excellence for navigation. What we do, a couple of different things. First of all, we track the spacecraft very carefully. We use Doppler and ranging to measure its velocity and distance very precisely. We fit that to an orbit. And at the same time, we're solving for all the ephemerides, essentially the positional points of all the satellites and Saturn. And that's a daily process. As a matter of fact, we're going to do a very tiny OTM tonight, orbit trim maneuver tonight, based on latest observations, because we move, we're moving a kilometer or maybe a few hundred meters, just being pushed around by our own shenanigans as well as smaller forces. And so we're constantly tracking the spacecraft. And over the decades, we've hit comets. I got to say that the navigation at Saturn is one of the triumphs of modern interplanetary navigation because of the precision that we're able to do this. You could do the same thing with much coarser measurements, but you'd have to be carrying tremendous amounts of propellant because every time you miss, you got to fix it to get back on track. So I'd be happy to share a paper with you or two. We've got a lot of papers about this.
And one of the comments was the navigation is so good, it's allowed us to go closer and closer and closer to these targets until we came within just 50 kilometers of the south pole of Enceladus. And in fact, our closest flyby was 25 kilometers, but it just wasn't under the pole. So we have just gotten so good we can go close, know where we're going to hit, and we don't miss.
Thanks.
I have some online questions here. Just want to go through a couple of those. A question from Titan82 wants to know, what is the temperature of the subsurface ocean of Enceladus? Well, if it's true that we have hydrothermal vents, it might be as high as close to boiling point around those subsurface vents. But clearly, if the water is a liquid, even though it's under a little bit of pressure and perhaps with some ammonia, it must be very close, it must be above the freezing point of water. So we know that otherwise the ocean wouldn't be a liquid. The next question is, will Cassini be able to photograph the vertical ring structures as it passes through the ring plane? That's a great question. Unfortunately, the answer is no. We can't photograph these vertical structures very well because they aren't very, very big. We don't think we'll have the resolution to resolve something that's a kilometer or less. And we don't think there's vertical structure in the C ring and D ring where we'll get the very closest to the ring. So I'm sure we'll be looking, and in fact we have looked as we've gone through the ring plane crossings. I don't think we'll have the resolution to be able to do that. And then the sun, if we really want to look for shadows, which is a really great way to look for structure, during this point in the mission there'll be no shadows cast by the ring particles. We're not at Equinox, so. Okay, are there any other questions? Okay, if not, thank you very much.
Thank you very much.
One down, one to go.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. May the 4th be with you. Wow. I got a live long and prosper sign right there in the back. Thank you for joining us here at JPL, and thank you for joining us at home for the Von Karman Lecture Series. Now let's get to it. The Cassini mission has revolutionized our understanding of Saturn, from its complex rings or magnetic environment to its menagerie of moons. Icy jets shoot from the tiny moon Enceladus. Liquid ethane and methane dominate Titan's hydrocarbon lakes and seas, and Hyperion has a static charge. We look forward to the puzzles Cassini will solve as it goes out in a blaze of glory. Tonight, our guest will reveal some of the recent science discoveries and share the excitement and challenges expected during Cassini's final orbits. Now, Dr. Earl Mays is the Cassini program manager, a veteran of 32 years at JPL. He began his career working on the navigation and engineering teams of the Galileo mission to Jupiter. After Galileo's final Earth flyby, he transferred to Cassini as a spacecraft operations manager and then deputy program manager. He left the project for 8 years to hold management positions in guidance, navigation, and control and avionics, then returned to Cassini as program manager in January of 2013. Now, Dr. Linda Spilker is the Cassini project scientist and co-investigator on the Cassini Composite Infrared Spectrometer team and has worked on Cassini since 1988. Since joining JPL almost 40 years ago, her first and only job out of college, by the way, she has worked on the Voyager project, the Cassini project, and conducted independent research on the origin and evolution of planetary ring systems, while also supporting proposals and concept studies for new missions to the outer planets. She enjoys yoga and hiking, especially through her favorite park, Yosemite, and is married with 3 daughters and 5 grandchildren. Right? Ladies and gentlemen, going out in a blaze of glory.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Its program is in. Its program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Cassini is on a collision course with Saturn. In the next 4 months, every week, we'll be coming a little bit closer and a little further away until finally on September 15th, very early in the morning here, about 3 a.m., it will enter the atmosphere, going at about 75,000 miles per hour. At that speed, the spacecraft won't last long. It will quickly lose control, begin to melt, and eventually vaporize into the very planet that it went to explore some 20 years ago today, 20 years ago. So you might wonder, you know, is that such a hot idea? I mean, you've got a perfect spacecraft. You've been rewriting the history books and the science text ever since you got there, and in fact, even beforehand. Well, for the next maybe 45 minutes or so, Linda and I are going to try to at least explain why we not only think this is a good idea, but a great idea. So quickly to the pad and beyond, as the movie showed you. We launched in 1997, absolutely flawless, a beautiful launch from the Cape on a Titan 4B. And 6.5 years later, after a very circuitous tour of the middle and outer solar system, we finally arrived at Saturn on June 30th, 2004, and had an absolutely flawless orbit insertion. For the next 13 years, we were doing pretty much this. Now, don't be alarmed. This is something we call the ball of yarn. This is the entire mission, all 293 orbits, some of which we haven't finished yet, beginning with SOI and continuing on. What happens here is that for the last 12 years, we've been using Cassini's rocket fuel and Saturn's largest satellite, moon, Titan, which is a mission designer's dream, to move us all through the Saturn system. So we've been able to, probably can't see it in here, but right in the middle of all this, there is Saturn. So we've been able to actually go to these very highly inclined orbits. So we come down over the tops and look at the rings and look at the poles, at these very long looping orbits out to examine the magnetosphere way outside of the influence of Saturn itself. And then, of course, these in tight orbits to investigate Enceladus and the icy moons. So for the last 12 years, up until last November, this is pretty much what we've been up to. A fascinating tour and an amazing set of discoveries. We'll get to a little bit of those later, and I think Linda will show you even more as we move on. But I want to jump back to the reason that I started with this whole premise of why are you doing this? Well, Saturn's got some ocean worlds. These are pictures, essentially Voyager-class pictures of the moon Enceladus and Titan, both mysterious in their own ways. Titan enshrouded by this veil of orange haze that we couldn't penetrate, and Enceladus exceptionally bright, but quite small, 300 miles across, so essentially a bright snowball. Well, by the time we were done, or Cassini was done, I should say, I'll take some credit, but not all of it by any stretch, Enceladus had turned out to not only be differentiated, but to have plumes, a warm global saltwater ocean, and hydrothermal activity. And if you notice that we just had a press release not too long ago that there is atomic hydrogen out in these plumes, all the ingredients for life on this little tiny moon. Absolutely earth-shaking discovery. Sorry, it's a bad pun. But really, just everybody was floored. We had no idea this was going to happen. And then on top of that, Titan was revealed to have lakes, a hydrologic cycle. Of course, it's not water, it's methane and ethane. Rain, clouds, rivers, estuaries, and it too kept as pristine as we possibly can. And I got to say that there's something about Cassini that, while it was a perfect spacecraft, it's not all that perfect. Well, we're out of gas. There's very little fuel left. And what happens, even though we were able to use Titan, as I showed in the other slide, quite effectively to move around in the Saturn system, we still need the propellant to keep the spacecraft oriented and on track. So without propellant, eventually it would be running out of control. And as we've come to discover with Titan and Enceladus, an uncontrolled spacecraft encountering these moons could eventually result in an inadvertent impact, which would cause us all sorts of embarrassment and some concern for future exploration. So we have to do something about it. And what we decided to do was what we've called the grand finale. So let me back up a little bit and talk about these are the final 6 years of the mission without the F-ring orbits. When we were discussing various options for the eventual, there's no euphemistic way to put this, the eventual disposal of Cassini, a lot of different options became available. But the one that just absolutely was most compelling was to actually stay inside the Saturn system, investigate as much as we can, use all the gas we possibly could, and then put it into Saturn. So this is what we've settled on, and as I think I'm going to try to continue to lead you towards the fact that this is an absolutely phenomenal end to a great mission. So this, again, is the ball of yarn, if you will, for the last 6 years. This began back in 2010. And what we've been doing, as you can see it even better here, every one of these little nodes, these little knots, is a crossing of Titan. And Titan has been moving us all through the system as it did for the previous 6 years. And what happens next, though, is really fun. We find a Titan orbit, and the mission designers have just been absolutely brilliant with this, found a Titan that took us into what we call the ring-grazing orbits. These orbits actually are in tight and are grazing tantalizingly close to the F-ring right here. 20 of these, and we just finished them up a little while ago. Absolutely phenomenal set of orbits that have provided entirely new insights into the rings and some of the ring moons. Better than we've ever been since SOI, and closer than we've ever been since the orbit insertion. We've never been in this close again before. So, well, what do we do next? There's one more Titan flyby coming. This is the final of the F-ring orbits. Now, what I want you to look for is a Titan flyby that's going to come sneaking around here and give us one last little push. This is the last orbit. Boom, around the F-rings. Now watch it. Here it comes. Here comes Titan. And watch what's going to happen to our orbit. It's going to suck just a little tiny bit of energy from Cassini. Just enough to put it between the rings and the planet. First of our ring plane orbits. And that's number one. We just did number two actually Tuesday, and we've got 20 more to go. Those are the grand finale orbits. It's an absolute pinnacle of astrodynamics and science achievement, so very exciting. Let me just give you another quick glimpse of these. This is going to be all 22 of them, so hang on for a while. But what I wanted to show you is that Titan has been our friend and moving us all around for the last 13 years, and we're calling this final Titan flyby the goodbye kiss. It is coming in right now, and it's we're going to slow down just a little bit after 22 of these. Titan's going to come squirreling in from the side. There it goes right there. And what that's going to do is it's going to steal just a little bit more energy. Just enough so that Cassini is going to go into the planet itself. That's the 75,000 mile per hour hit a brick wall kind of encounter that the spacecraft will not survive. And again, the point is that we absolutely must put the spacecraft into a position where it can inadvertently contact either Enceladus or Titan or any of the other icy satellites, which we believe are also potential for further exploration. So let's just see how we do here. All right, so we've got the orbits, right? We've got a challenging new set of orbits, a whole new regime, but we've got an old spacecraft. So the first question we've got to ask is, can we teach this spacecraft new tricks? It's going to go into a new region. It's going to do different things. And of course, with any kind of learning experience, there are constraints. We've got folks on the science side that say, look over here, look over here. The Saturn's really cool. On the other side, they're looking at the rings. No, look over here. And then you've got the engineers. I probably consider myself one that's saying, you got to be bold. You got to do, dare mighty things. Well, wait a minute. We ought to be careful. It's dangerous over there, and it's dangerous over there. So what's going to happen? The spacecraft, of course, is, I'll do what you tell me. Just got to tell me to give me the right orders. So it's a bit of confusion. Let me just try to answer the question that we've tried to deal with between the bold, the mighty things, and be careful not to do anything too crazy. And that is the gap. There is a very narrow gap. It's 1 billion miles away, so a 1,200 mile gap is kind of narrow. And it's been a big deal for us to worry about this. And so let me just give you a couple of animations that one of our mission design engineers put together, which really, I think, give you an idea of what's going on here. These are the 22 orbits, and this is the final orbit. And here is actually a pretty nice and pretty accurate rendition of Saturn and its rings, an artistic representation. Here is what it looks like with a high contrast photo. So you can see we are flirting very close, the atmosphere on one side and the dust on the other. So it's not quite as easy a shot as it first appears. If you now take a look at this a little bit closer up, you get a bit better view of our ring plane crossings and our periapses, or minimum altitudes, which are all in the southern hemisphere of Saturn. One last look, and you can kind of look down the orbital path, and you can get a sense of just how close these are to the Saturn itself, and how much Titan, who's still out there pushing us around, is moving these various orbits around. And then finally, you see our final orbit over in the end. It doesn't show up well here, but it's there. So what do you do with that? Well, first thing we engineers do is we put that into an XY chart, right? What else would you do? It's data. And so here are our minimum altitudes, and here are XY plane crossings. But then, of course, what you want to do is put your boundaries on. And what we've done is we've more or less decided that the extensible edge of the D-ring is about 6,400 kilometers from the center of Saturn. And we picked some orbits that we thought were pretty cool. They've got a lot of moving around in here. They go down into the atmosphere, and then finally down here you'll notice our final orbit. But they do some things up here that are a little bit alarming. They take us up into the dust. So we had to figure out what we're going to do about that. There's a high contrast photo again of the dust, and there's that boundary, and there's the range that we're in. So we had to come up with some sort of scheme as to how to deal with the dust. We've modeled it completely. We feel like it's safe in all the models that that the ring scientists have, and we've got the best ring scientists in the world, as you could imagine, on the project. So we really didn't have a lot of worry, but you never know. We've never been there before, so we had to see what was going on. And so there's the region we were trying to avoid. And what we decided to do for these up here was shield them. Now, if you notice the images of Cassini, it's got a large, well, it's right over there. There's a very large saucer-shaped antenna on the front. Pretty solid piece of material, and almost all the instruments are behind it. So if we go into the dust with that antenna pointing into the dust, everybody's pretty fine, except, of course, for that long magnetometer boom, which is exposed. But there's not a thing we can do about that. So for these crossings, we decided that we would protect the spacecraft by the shielding. Furthermore, since we really didn't know where we were going, or, well, we knew where we were going, we just didn't know what was in there, we decided to put a shield on our first flyby as well. We've now completed that flyby and completed, I'm calling them flybys, they're ring plane crossings. Completed that one, and I happy to say the spacecraft's come out just fine. So let me show you just a little bit of what that looked like. This is our first crossing, right? And you're going to watch the spacecraft reorient itself as it goes through the dust and point the Huygens antenna right into what we call the ram direction. That is the direction of oncoming dust. And of course, being as opportunistic as we can, the minute we're through the dust, we turn the spacecraft back around and start imaging the planet again. So just for a few minutes on either side of the ring plane crossing, we use the spacecraft antenna as a shield for the rest of the instruments. That went perfectly fine. Now, you want to see some drama. It's not this. It's me trying to make it work. I'm going to see if we can do this. This is, well, let me explain it a little bit first because I'm going to mess it up. This is the, what we call the radioplasma wave spectral analysis of the ring plane crossing. And what happens is, as dust strikes the spacecraft, it creates a plasma. It's an ionized gas, and our antenna can pick them up. And so the more dust you run into, the more energetic, more plasma you get, and you get exactly what you'd think you see. This is time, and this is, in a certain sense, a measure of the plasma or energy. And so you see a very high peak right here at the ring plane crossing. This happened during one of our F-ring grazing orbits, and it was just classic, ring grazing material. So what I want to do, if I can get this, I can find my mouse here. Oh, there it is. So this is the sound file of what we consider a normal dust crossing. And you can see the little line going through. So you can see hear both some of the low-level particles, the kind of the smaller particles. Every now and then you hear a larger bip of a more energetic or a larger particle striking the antenna. That was with the high gain antenna shielding us. So here's what we saw during our first proximal orbit passage. After all these dire concerns about the dust, I'm not going to spend a whole lot of time trying to find this audio file that doesn't sound like anything, because this was absolutely silent. We had the noise turned up so we could just find something. Turns out that all of this drama about the D-ring and all of that dust in between that gap was actually just a big empty. We don't quite understand it. Well, I should say the ring scientists are still befuddled by it. There shouldn't be that little dust there, but something's cleaned it all out. So I think as one of our mission design folks quipped, Saturn has swept the doorstep free for us, like a good host. So indeed, so far, we've had perfect ring plane crossings, and the drama about any dust issues or things like that seem to be for naught. Okay, so we've just talked a little bit about how to avoid the dangers using the high-gain antenna and things like that. Now, what about, look over here, look over there. We've had 22 orbits. Sounds like a lot, but we've got 11 functioning instruments and 5 other investigations that try to share instruments, and there's a huge amount of conflict between this. And so it was very heartening. We started working on this years ago, that the instruments figured out new ways to use and cooperate on these 22 orbits. For example, we have the gravity folks that when we're doing gravity science, they want to have the antenna pointing to the Earth. And they want to have it rock solid because they're trying to measure incredibly subtle variations in the signal as it passes between the rings and Saturn. The magnetometer folks want to roll because they want to spin that big boom through as much space as they possibly can in order to get the best magnetic field data. Well, they found a way to spin on an axis that keeps the radio bore sight directly pointed at Earth. And so they get to spin, and gravity science gets the benefit of their, again, a beautiful collaboration. We figured out a way to repurpose the INMs to become an atmospheric probe. The spacecraft can now use the data that's on board, normally stored on board, and shoot it down immediately. So as we're burrowing into the atmosphere, we're sampling data to the very last instant. There are bunches of examples of that. So let me just go to this last slide. This, again, is all of the periapsis passages all along here. And as you can see, they are spread around, but we really had a tremendous amount of contention. And what happened was that almost all of them shared. Instruments are collaborating on all those circled orbits. There's collaboration between the radio science and magnetometer, between dust and mass spectrometers, it goes on and on. So we've maximized every piece of science that we can get out of these orbits. And with that, the amount of time I've wasted, here is the Cassini poised for its first flyby, and I'm going to segue into the grand finale objectives, some of the unique science, and put Linda Spilker on. Thank you for your patience.
Okay, well, I'm Linda Spilker, and I'm the Cassini project scientist, and I have a really cool job. I get to coordinate amongst 300 scientists spread around the world to get the best science possible for the Cassini mission. And I've been lucky enough to be with this mission for a long time. It's been almost 30 years that I've worked on Cassini. In fact, my oldest daughter, Jennifer, just started kindergarten when I started working on Cassini. And now she's married, and she has a daughter of her own. And what's so amazing is how quickly those 30 years have flown by. And in fact, here's sort of, basically I've been on the Cassini mission for one Saturn orbit. It takes Saturn about 30 years to go around the sun a single time. And so what's shown here are the mission phases as a function of Saturn orbit. So you can see we, as Earl said, we arrived in 2004, had a 4-year prime mission, 2-year Equinox mission. We're now in our 7-year Solstice mission, and we're at the very tail end. As Earl showed you, we had just finished our ring grazing orbits, and we're now 2 dives into the grand finale. So what I'm going to do is I'm going to step back and show you some amazing pictures and science results from those ring grazing orbits. We basically pulled Cassini's orbit in very close to Saturn's F ring, which is nestled right against the main rings, giving us a chance to get incredible pictures. In fact, if you look in the blue region, we could get incredible pictures of tiny little moons that orbit in the gaps in the rings, next to the rings, and the best pictures ever of the rings themselves. So here you can see a couple of gaps. The wider gap over on the left, that's the Encke gap, and inside of the Encke gap is the moon Pan. Now, Pan was actually discovered in the Voyager data, but not until 10 years after the Voyager flyby, where Mark Showalter put together the images and figured out there was a moon and where to look for it. The next gap out includes a little tiny moon named Daphnis. Cassini discovered Daphnis in 2005. And finally, out hugging the edge of the A-ring is Atlas. And Atlas was discovered in the Voyager data as well. So to really see these little tiny moons, it takes a spacecraft. So let's take a look at those. First, let's look at Pan. Here's a movie that we took with the Cassini spacecraft. These are raw images. You can see cosmic ray hits and so on. But here, I'll back it up and show it again. We went zooming by this tiny moon. And you can see it looks unusual. It doesn't look like a potato. It doesn't look like a round moon. In fact, here's a couple of views of Pan. Pan's about 20 miles across at its equator. It's nestled in a 200-mile-wide Encke gap. And you can see it also has this very interesting equatorial ridge or skirt of particles. And what it does is it's accumulating particles from the edges of the Encke gap, and they go around the equator of the moon. And sometimes those particles actually slide out. It's hard to see here, but there's actually, you can see a landslide of particles in a couple of places where they slide down onto the main central frozen moon itself. You can see tiny little craters, some ridges inside of along this ridge here. So very interesting and unique. In fact, one of the Cassini scientists said, that reminds me of cheese dumplings. So you can see the edges on these cheese dumplings. So a very, very unusual shape. Well, it's moving on to Daphnis. Daphnis is much smaller. Daphnis is only 6 miles across. And it's holding open a 25-mile wide gap. Turns out that these moons are big enough they literally shove aside the ring particles and create a gap that goes all the way around Saturn's ring. So if you're a big guy, you get in the rings and you say, move out of my way, and you can create a gap. Daphnis also, as well as Pan, creates waves along the edge of the gap. Here's another view of those waves. You can see actually a tiny tendril of ring particles that Daphnis has pulled out. And just like the waves in an ocean, you can see this wave going along and slowly damping out, and the particles actually shearing apart. So just very beautiful, very close-up views, incredible detail in the rings themselves as well. Let me go the right direction. And this is a movie of Atlas. Now, Atlas is the moon. It is about 26 kilometers across and only 11 miles north to south. And so you can see here's a close-up view of Atlas. It's not washed out like this on my screen, but it's much smoother, very few craters. There's a big icy particle in the center. It turns out these moons can't accumulate ring particles forever. They get out to a certain size, and then their gravity gets balanced by Saturn's gravity. So any ring particles that try and stick get pulled away by Saturn's gravity. So Atlas has grown pretty much to the biggest size it can around its equator. And here are the 3 moons shown to scale. There's a scale bar of 6 miles. So you can see Daphnis truly is tiny. And it really took Cassini's very stable, good cameras to be able to find tiny Daphnis. Now here's one of my favorite pictures. This is going all the way back to 2009. The sun was edge on to the rings. And at that point in time, basically the sun's edge on, at that point in time, anything that sticks above or below the rings will cast a shadow. And that's called equinox. And so you can see shadows, many, many, many shadows, cast by objects probably 1/3 to 1/2 mile in size, probably accumulations of particles, maybe bigger particles as well. But we've never been able to really resolve or see one of those particles up until very recently. This is the same view now turned sideways. Here's the edge of the B ring, and you see all of this speckling. And those are individual clumps now that we can resolve at the edge of the B ring. Incredibly detailed structure. We were thinking as we got to higher resolution, the ringlets would just appear to get wider and we'd see more structure, but instead we see more and more ringlets. Every time we get closer, the ringlet that's there divides into more, and it's just an incredible detailed structure. Now, I got this picture from Matt Tiscarino, and he tried something very clever. He realized if you could fold the picture over, essentially, along a line that's perpendicular to the rings and subtract the 2 halves, anything that's different as you go along the azimuth in this direction along the rings would show up as additional speckling. So he did just that, and you can see, of course, the edge of the B ring has lots of these little speckles. It's very different as you go from one place to another. Slowly dies away, but then there's a couple of other places that have a lot of speckles in them too. And it's very sort of hidden away in that other image, but you can see them now, and so now we have to explain why can you get clumping so far away from the edge of the B ring. So lots of new science in just a handful of pictures that have come back in the ring grazing orbits. And then, of course, these very interesting objects called propellers. If you're a tiny moon, you're not big enough to make a gap. What these propeller objects are trying to do, there's an object in the middle here trying to open up a gap. It gets a partial gap. Those are the two arms of the propellers. And we had a lot of fun. We named the propellers after aviators. So you'll find an Earhart. In this case, it's Santos Dumont. And you're seeing a view on the lit and unlit side. This is about a mile across in width here. The object is probably a quarter mile or so in size. And so these objects are like the seeds that you would have in a disk from which the solar system formed. So Saturn's rings are really a laboratory where we can watch dust interacting, how you could grow larger objects, planetesimals, that could go on to form a solar system. So studying the rings gives us ideas about how our solar system formed and how you could get solar systems around other stars. So very exciting to look at as well. And this is a very interesting picture. This dot here, it isn't a star. It's not a cosmic ray hit. That's the Earth. That we turned the Cassini cameras on April 12th to take our last picture of Earth in between the edge of the A ring and Saturn's F ring. And if you look very carefully and blow it up, there's the moon. So you're actually seeing the Earth and the moon. And if you're on the Earth, this was over the middle of the Atlantic Ocean when we snapped this picture. So it's a very special time. We have to use Saturn to cover up the sun so we can turn our delicate cameras close enough to the sun, but the sun's covered, to take this very unique image. So this is our farewell picture, our last picture of the Earth. Now, Earl showed this. This is the historic first passage. This is the start now of the grand finale, going in between the rings and the planet, flying in a place that no spacecraft has ever flown before. And that's very exciting because every time you go someplace new, you're going to make new discoveries. And that's exactly what Cassini did. If you're riding along with the Cassini spacecraft, here's what it might feel like as you're peering over the edge of the antenna to dive in between the rings and the planet. You're going at 76,000 miles an hour, and it only takes you an hour to go from over one pole of Saturn to over another. And then you come back out the other side, and you do this every 6.5 days. So you're coming in very quickly. You can see the background of the Milky Way. You come out the other side. You can see the sun here as you go on out. So just a very exciting time in the mission. So what did we see on that first dive? We actually, on this first dive, we used the high-gain antenna to protect the spacecraft, but we rotated to point the cameras at Saturn. We started at Saturn's North Pole, and we just kept taking pictures every 17 seconds from the North Pole down toward the equator. And here you can see views of some of those. Here's the giant vortex, hurricane-like, right at the North Pole. Some of these clouds that are better resolved than we've seen before. Here's the edge of the giant hexagon, a 6-sided jet stream that's 2 Earth diameters across, centered on the North Pole, then down to some of the other images. So I'm going to show you some of the other additional ways to look at this data. One is here is what the spacecraft was doing as we were taking those pictures and looking at Saturn. So you can see that we're going down. You can watch those little picture frames getting smaller and smaller and smaller as we go down. You'll see shortly a turn as we point the high-gain antenna down into the direction of particles, but we're still taking pictures. We're still taking science data all of the way through. Here's another view. I like this view because the red dot is showing you where you are on Saturn, and here's those pictures as if you're gazing out of a tiny window looking down on the planet. So you can see all of the detailed structure. These are all up on our webpage if you want to go and take a look at those. There's the turn for the high-gain antenna, and we'll stop here shortly. And then just to, this is just really an up-close view of those first pictures that came back. And we were gathered on Wednesday night. It was just, a little over a week ago We were gathered to wait for the first dive to come through. It was actually on April 26th, which was my birthday. And what a great birthday present to make it through successfully through the rings. So that was really a good day. And as we watched these pictures come back, lots of us were here until about 2 in the morning or so. One of the leading Saturn scientists, Andy Ingersoll, said, "I've never seen anything like it in my life. I don't know what it is." And that's half the fun. You go there and you're not sure what you're going to find. Now this is the second dive. What you're seeing here is a movie. It's showing the Cassini spacecraft along this orbit. It'll cycle a few times. Here, let me back it up. It'll cycle again. Here's Cassini. This is the magnetic field lines. The strength is color-coded. And we're turning the spacecraft. This is showing you an hour. And we're turning Cassini the whole way through that time. And that's to calibrate the magnetometer and get back data. And we were clever enough to have just the right instant in that turn to have the cosmic dust analyzer looking in the direction of the ring plane. Our hope was it would sample the ring particles and give us composition. But as Earl said, it's pretty empty, and so there wasn't a lot to see for that time. Here's some pictures that came back. I just went to the web and pulled off a few of them. This is a star, and this is what happens when a star gets overexposed in the cameras and is extra bright. Here's the F ring, and then here's part of Saturn's A ring. Another one of the F ring, it's very kinky and clumpy, very unusual. We took a very long movie as we flew through on this particular pass of Saturn's F ring. Let me give you some of the highlights of the science that we're going to be doing in the remaining 20 dives between Saturn and the rings. Well, of course, it involves the planet itself and the rings. If we start with the rings, one of the things that Cassini can do is for the very first time measure the mass of the rings. Right now, that mass is uncertain to 100%. We don't know what it is. But by diving in between Saturn and the rings, we get just the mass of Saturn by itself. Earlier in the mission, we have the mass of Saturn plus the rings. Subtract the two, you get the mass of the rings. Now, if the rings are more massive than we expect, then they could have perhaps formed at the same time as Saturn. They could have been massive enough to have survived the micrometeoroid bombardment and erosion that took place to be there till today. Less massive, they must be young. Perhaps only 100 million years old, a small fraction of the age of the solar system, perhaps forming from a comet or a moon that got too close. Saturn's gravity ripped it apart. Those pieces went on to form the ring. We still hope to get the composition of the rings. We just have to get a ring particle into our cosmic dust analyzer. Then for the planet itself and also for the rings, we'll get some of the best pictures ever of the hexagon, of the storms at the poles. You've seen one swath. We're going to do that again, perhaps get some color, exquisite pictures of those inner rings. Who knows what we'll find when we take a closer look. Then, of course, on the last 5 orbits, we're literally dipping our toe into Saturn's atmosphere. And our ion and neutral mass spectrometer will be tasting the composition. It's mostly hydrogen, but there are other things there as well. And so for the first time, directly sampling the upper atmosphere of the planet. There's a radiation belt there. We know from Saturn orbit insertion there's a very weak radiation belt, not nearly as strong as the main belt outside of the rings. So we hope to characterize the radiation belt and the plasma environment in that gap between the planet and the rings. Then, of course, we're going to study the magnetic field, these blue lines coming out from Saturn in exquisite detail. One of the things we still don't know is the length of a Saturn day. How fast does Saturn rotate on its interior? Because when you look at the outside, all you see are clouds. And different latitudes rotate at different rates. And so we want to know what's the rate of rotation. It's around 10 hours, maybe 10 hours, 20 minutes. What is it? And we're hoping if the magnetometer data shows us the magnetic field is tilted just a little bit, it'll swivel around like a giant lighthouse, giving us the length of a day. We also want to know, where does the magnetic field originate? The atmosphere is gas at the top. That hydrogen compresses to be a molecular hydrogen liquid, compresses some more until it becomes metallic. It's metallic in a phase where currents can flow and generate a magnetic field. We think it's about half a Saturn radius in, about 1 million atmospheres of pressure. That's what our models tell us. So we'll get a chance to find out, see what the inside of the planet is like. We'll study the aurora in more detail. Particles come in along the field lines, crash into that area, create aurora, and they're pink and purple, because it's hydrogen that's glowing and emitting in the aurora on Saturn. And then finally, looking at the interior itself, with our gravity measurements, the size of a rocky core. Is it 1 Earth in size, 2 Earths in size? What's the boundary like? How deep do the winds go? Is it 300 miles, 3,000 miles? When do you start to feel the winds peter out? And we think with the gravity measurement irregularities, we'd be able to pin down the location of those winds. Then, of course, on that final orbit, we go into Saturn. And that's going to be a really, I think, a tough day to say goodbye to this spacecraft that's been around for so long. And when you think about it, with Cassini's final heartbeat, that's humankind's last intimate personal connection with Saturn. That connection will be cut. And we'll no longer be able to see those little tiny moons that I showed you pictures of tonight, or Saturn's F ring, because you see, they'll be lost in the glare of Saturn and its rings. Except for once every 15 years, when the rings are edge on to the sun and the rings go dark, then we'll get a chance to catch a glimpse of these little tiny worlds that Cassini revealed. But we have 20 more dives through that gap before we get to the end. So we have a lot more new, exciting, incredible science ahead. So join us, check our webpage, look at the great pictures coming down, and enjoy these final heady days of Cassini's grand finale. Thank you very much. Earl and I'd be happy to take questions. If you wouldn't mind, please using the microphone in the back, and that way everyone will be able to hear you. So if you can go in the back and use the microphone, that would be great. Go ahead.
Yeah, in the early 70s, I, along with two now retired colleagues, developed the model for the gravitational attraction of a disk, which Voyager navigators said was rather critical to Voyager actually to go to Uranus instead of some random place. I'm kind of surprised that partial derivatives of your trajectory with respect to the mass of the rings using that model don't give you better information than 100% of an error bar.
Well, sort of the question is, you need to know the mass of the rings to have sent Voyager onto Uranus, so why don't we know them better from our navigation data? Well, if you look at it, the mass of the rings compared to the mass of Saturn is absolutely tiny. So in a certain sense, the rings are kind of in the noise because Saturn is so massive. So even after all, we have it down much more precisely than we had for Voyager, but it's still a large error bar.
Another question also. I assume that when the line of sight between the Earth and the spacecraft passes through Saturn, that you are getting information of the atmospheric composition using microwave spectrometry.
Right. That's a very good point. There are other kinds of things we'll be doing with the spacecraft. We can actually use the radio signal occulted by Saturn to get occultations of the atmosphere, of the rings themselves, and do a lot of other science focused on Saturn as well. We'll actually get radar on the rings for the first time, too. And we've been doing that throughout the mission, using the radio beam or stars to get occultations of the planet and of the rings.
Thanks, Lon.
Hi, I'm curious if you could talk at all about how you made the determination that it was going to be safe to pass between the rings and Saturn. I know you talked a little bit about the ring scientists did a lot of work in determining that the dust environment would be low enough Cassini could survive, but since it had never been explored before, how could you make that with enough confidence to say, yeah, we'll risk it and let's go?
Well, we had a model, and what we did is, Earl showed it earlier, we took a picture of the innermost part of the rings with Saturn's shadow going across it. And we knew the shadow was very black and very dark. We looked at our image, we stretched it to see where that boundary went relative to the shadow. But in the images, all you see are the tiny dust particles. So we felt we understood the dust very well. But the bigger particles, if there aren't very many of them, you don't see them. So we were just sort of assuming, okay, let's assume it's sort of like when we go through the E ring or the G ring, just little particles and extrapolate in. Our extrapolations told us we should have less dust than we saw in the E ring or the ring grazing orbits, but there was nothing in the model to say there'd be no dust. So, but part of it, the bigger particles, that was a risk though worth taking.
Thank you.
Thanks for the great talk. I had a question for each of you. First question, on the animation depicting Cassini's first travel through the ring plane, it appeared that the mag boom was rotated towards the D-ring. Is that accurate, and would there be any difference between particulate risk on either orientation?
No. When you're pointing into the ram, the mag boom is equally exposed, and so that was a preferential attitude for the magnetometer itself. So.
Yeah, if you look at the Cassini model over here, you can see the mag boom, that big golden boom. It doesn't matter how you point the space. Well, for the high gain antenna protecting the rest of the spacecraft, the mag boom is hanging out there. Yeah.
Second question, on the Equinox slide that you had, there's a lot of vertical perturbations, and it looked like they were all 90 degrees from ring plane. What are the mechanics behind that?
Well, in that image I showed from Equinox, the sun direction was shining from above, shining down. And so that small piece of the rings that you saw, it made them look like, all the shadows were going out in a single direction. Why the clumps happen to be at the edge of the B ring, there's a resonance keeping the edge from spreading, and maybe the clumping, there's a lot of clumping that happens in that region as the particles, like a crowded freeway, they're trying to merge over and they can't, so they're starting to clump together.
But the main question was on the vertical extension of that. If a moon is traveling by and caused a perturbation, wouldn't that be bent or inclined as opposed to straight out of ring plane?
Oh, everything pretty much at Saturn. It's a very interesting question. The rings on average are only about 10 feet thick, and Saturn's oblateness tends to keep everything very, very coplanar. So they don't tend to have inclined orbits. There are other places in the rings with inclined orbits, bending waves, et cetera, but not generally across the rings, not at the edge of the B ring.
Thank you.
Yeah.
Yes, all the orbits of the spacecraft that I saw here looked extremely elliptical. Is there a way that you could have obtained a circular orbit? And if so, could you have continued the mission by attaining a circular orbit within the ring gap, considering now that you know that there's very few particles in there, and then you wouldn't have run into much resistance, and if it eventually decayed its orbit like a satellite around Earth, it would just crash into the planet anyway, and it wouldn't present any hazard to the moons.
Well, I think a circular orbit's always an option, but not a very scientifically interesting one. One of the things we really did have to, if you're going to use Titan as a circularizer, and that's really the only way we could have done it, you're going to have to come back to Titan. There's no way to avoid it. So you're essentially going to be in some sort of Titan-like orbit. And if you're going to be doing that, you're eventually going to have to deal with the fact that you're out of propellant and in an orbit you don't want to be in with Titan messing with you. There were some other options for very large elliptical orbits that were also stable, but the scientific value of those relative to these grand finale orbits was so marginal that they were dismissed almost immediately.
Right. In fact, the scientists kind of looked down this table of options of what we could do, and they saw the grand finale, and they said, that's it, end of discussion, we don't need to talk about it anymore. So they like that.
Yeah, granted that because of the way the mission proceeded, it's no longer an option. But if you'd known when you started the mission what you know now, would it have been possible to end the mission with a spacecraft in a circular orbit within the ring gap?
Oh, within the ring gap?
Yeah.
I don't think so. Simply because where are you going? You're going to have to find something to circularize you at both the periapsis and at the apoapsis, and I'm not quite sure. I'm not going to stick my neck out on that, though. Again, if you're using Titan, and that's really the only thing we've got, you're going to have to end up coming back out to Titan again.
So there's no way, you couldn't carry enough fuel to do that? You'd have
Well, that would be the thing. And no, I don't think... Well, I'll let Linda speak to the scientific merits of carrying that much propellant and then using it to go inside the rings and stay there. But you could. I mean, conceivably, you could take enough propellant to go in and actually, once you've got periapsis inside, then do a braking burn to take apoapsis in as well. But that's a lot of propellant.
A lot of propellant. Or you could try aero capture or aero braking. But until Cassini flew there, we had no idea how clear it would be.
Okay. Thank you.
Well, that's, yeah.
Hi. I was wondering, do you use plutonium to power Cassini?
Yes, we do. But we use plutonium in a very interesting way because plutonium, that's P238, is very hot.
Yeah.
And so all we're doing is using the heat from its radioactive decay to power little thermoelectric cells. We have 3 of them on the spacecraft. You can look at the model later and see them at the bottom. There are these black things. And so it's the heat from plutonium that gives us the electricity. And that's all we use it for. We actually use chemical rockets fuel for the propellant. And the plutonium well, as a good example, Voyager's coming up on its 40th year, and they're still going fine on plutonium. Cassini has lots of electricity, just no propellant.
Yeah, if you look at the Voyager model, that big black object off to one side, Cassini has 3 of those. And that's what contains the plutonium that the heat is used to power Voyager and to power Cassini.
Another question is, do you have an idea of what the Pentagon could be made of?
Oh, what the hexagon at the North Pole is made of? Well, it's a jet stream, so it's made of gas, but going around very fast. That edge of the hexagon is like a giant racetrack, and the clouds just race around there faster than just about any place else. Why it has 6 sides and what keeps 6 sides on it, we have no idea.
Thank you.
Yeah, I was wondering if the ring gaps seem to be always caused by moons that clear out the debris, or maybe moons that were once there and were ejected at some point, or are they like dynamic and constantly changing?
Well, initially with the rings, we thought that the gaps had to have moons because we saw Pan in the Encke gap, then we discovered Daphnis in the Keeler gap. But there are gaps in the C ring. Some of the gaps have ringlets inside of it, and we looked and we looked and we looked. We didn't find any moons in any of the gaps in the C ring. So there's some process that we don't understand quite yet that can keep gaps open without moons. So if you have a good idea, let us know.
Thank you.
Howdy. I actually had 2 really quick questions. One was about Pan, that odd ridge-shaped feature on its equator. Do you know like the consistency of that? Is it more of like a rocky material or more of like something equivalent to sand?
Okay, well, the rings are made 99% of water ice.
Right.
And that's also true of the moons. And we can also, through some mechanisms, figure out how porous how porous it is. An ice cube would be not porous at all. A snowball would be quite porous. Pan is much more toward a snowball than it is toward an ice cube. Okay. So there's a lot of porous space in between, and it's water ice.
Okay. My second question was in regards to the final orbit. Right now, the final orbit is is perpendicular to the rings. Was it ever considered to do a orbit more parallel to the rings? Was that ever a consideration?
Do you want to answer that?
Well,
the navigator? That's a good question. They did find something.
It's a great question. But what happened actually when we first started with Cassini, we didn't think we could do what we've done. So the techniques, the astrodynamic techniques and the numerical techniques have been evolving. And we actually do now know, based on some work from the Cassini navigation team, that we could have these so-called ring skirting orbits. But by that time, and interestingly enough, we developed the Cassini project, the nav team developed these responses more as we ran out of propellant too early. By that time, we had invested so much time and energy and our propellant reserves in getting ourselves into these grand finale orbits that it really wasn't an option. But it's out there, and we're actually seeing maybe some mission proposals next time around to do that.
Right. When Cassini launched, we had no idea you could dive in between the rings and the planet. And that just took the evolution of software and of the right people to find that. So actually, a group at Purdue first found it. Then people here at JPL were the ones that actually came up with and finished the grand finale orbits.
So it's possible that the next Saturn mission will be more ring focused or something along those lines.
There's almost a ring hovering type mission now that is, the astrodynamics allow it to happen. It just need to get it started.
So just sort of answer that. The priority is if we were to go back to Saturn, NASA has a New Frontiers program. And in it, there are 3 possible Saturn missions. One is a Saturn probe, send a probe deep into Saturn's atmosphere, measure Nobel gases and the composition as you go down. The next is Titan as a target, orbit Titan, land on Titan, float in Titan's methane seas. And the third is to go back to Enceladus. So those are the 3 major targets. New Frontiers is a much smaller budget than a big flagship like Cassini, but at least there's 3 of them, 3 possibilities. In November, they'll down select. I think they got 40-some proposals, go down to 3 to 5, and then further down select probably a year after that. So we'll see if Saturn is still in the mix, going back to Saturn. But it's still, it's probably 30 years from now until we get back. It's a long trip.
Fingers crossed.
Yeah.
Thank you.
I have a 2-parter also. First question is, how long out are you able to plan for this? Like a 30-year mission, how long are you able? I mean, do you start off with a 5-year plan and then you figure that out, and then after another 5 years, you do another 5-year? Like how much out do you end up before you reevaluate?
You pretty much plan end to end. You plan, when you're going to launch, how long the cruise is going to take, and what your prime mission would be like. And that's part of the package that you put together and give to NASA for the missions that you want to fly. So when we first Cassini started in 1990. We picked the instruments, built the spacecraft. We knew it would launch. We had some launch slips and things, but when it launched in 97, we knew exactly when it would get to Saturn. And we knew exactly what those 4 years would look like.
That Solstice mission that I showed you actually was planned in 2009, right down to almost the final set of orbits. Now, there are certainly some tweaks and modifications, but we really take the long view on that final set.
So I'm also curious, the crash into Saturn with Cassini, was there a plan B, and why wasn't plan B chosen?
Probably plans A through F, maybe through H. And again, it's the science.
Right, yeah, the science drove it, and more than that, the fuel light's on, it's red and it's blinking. And it's saying, you're almost out of gas. In fact, we don't use the main engines, we use the hydrazine reservoir now. And it really was the fuel. Healthy spacecraft, great instruments. We just need a way to refuel, and we'd be fine.
Thank you.
Do we understand why the Saturnian system is so complex compared with any other solar system or any other planetary system in our solar system?
Well, the Saturn system looks complex. You've got the main planet, you've got the rings and 62 moons. But the Jovian system has complexities of its own, as do the systems of Uranus and Neptune. We just haven't studied Uranus and Neptune as well as we've studied the Saturn system. Saturn just has these great, big, wonderful rings. But so do Jupiter, Uranus, and Neptune. They have rings too. They have fascinating moons, maybe not quite as many. But there's a lot of complexity with those outer planets.
In other words, it just happened.
Yeah, we don't know. That's a good question. Why the moons ended up, the order and the masses, that's a really good question.
Yeah, the same question for both of you. There have been many surprises on this mission. What was the biggest surprise for you?
I'll let you take that. What's the biggest surprise?
I guess I've still got to go back to Enceladus. I mean, there's just something absolutely magical about this. I mean, again, it's just totally out of the blue that it would be as dynamic as it is, and not only dynamic in a geological sense, but to have all the chemistry going on as well. I mean, that's rewritten the book. It's promoted itself from a class 0 to a class 3 object, and by those I mean planetary protection terms. It is something that, once in a lifetime, you're walking down the trail and you find a ruby, or it's just amazing.
Yeah, I mean, Enceladus was a complete surprise. A moon 300 miles across. We thought for certain it would be frozen solid. And to fly by and see active geysers coming out of 4 fractures at the South Pole, mostly water vapor and water ice particles, but you found organics, you found carbon dioxide, methane, ammonia, then the global ocean that was around the rocky core, hydrothermal vents on the seafloor. That hydrogen coming out has enough energy in combination with methane. In fact, a scientist did a calculation. There's enough hydrogen coming out. The energy there is the equivalent of 300 cheese pizzas per hour. coming out of, out of Enceladus. If you wanted microbes, you had a lot of hungry microbes. You have a lot of food there for them to eat. So basically, I think one of Cassini's legacies will be we've changed the way we look at where you can find life. It doesn't have to be in that Goldilocks zone where the Earth is, where you can have liquid water on the surface. It could be beneath the icy crusts of worlds like Enceladus, Europa, Titan, and perhaps other worlds. So I think that's probably the biggest shift in our thinking. Where do you go to look for life? And if we found life in Enceladus's ocean, it would be remarkable to think that life could form underneath the icy crust. It would be totally a different path from the life that we took on our planet. And by the same token, if we didn't find life in Enceladus's ocean, that would be remarkable as well. Because it would show you, here you have this habitat, you have these ingredients, and yet life didn't get started. And so maybe life on the Earth is special. So either way, whatever the answer to that question, whether it's Enceladus or Europa, it will be remarkable, whatever that answer.
Thank
you. Two quick questions. One, is there a contingency plan if any of these last orbits throw a wrench in the works or surprise? Sort of like not finding dust, maybe you find something you weren't expecting. And the second question is, in the sort of contingency planning, is there any thought or imagination as to what happens when you put a little bit of plutonium on a planet that probably didn't have it to begin with?
Do you want to take the first part? I'll take the second part.
I'm sorry, I got.
Oh, okay. The contingency plans. Once we got the final flyby of Titan, 127th flyby, we were put into what we call a ballistic trajectory. And if something happened to Cassini, the bits and pieces or whatever, or the damaged Cassini, would follow the same orbits, ending up in Saturn on September 15th. So we don't have to do anything else. And that's why NASA's planetary protection really liked this set of orbits. We could get in there, take the risk, something happens, the mission is still going to end with that. As far as putting plutonium into Saturn, if you look at the mass of Cassini compared to the mass of Saturn, it's pretty tiny. And one thing is kind of cool to think about, we're putting a little piece of Earth into Saturn. And we're going really fast, and it's going to be very hot, so if we do have any microbes there, they're going to be toast.
Thank you.
I have two more questions. One question would be, what would you do if you lost connection with Cassini?
You want to take that, Earl?
We would keep looking. Cassini, and that, I don't mean to be glib, but what happens if Cassini has a tremendous amount of what we call fall protection software built into it. So if we were to lose contact with Cassini, we have to talk to Cassini, and Cassini has to talk to us. If, for example, we lost contact and Cassini didn't hear from us, it would start looking for the Earth. And meanwhile, we're starting to look for Cassini. So we go through days and days and potentially weeks of allowing Cassini to turn on different hardware, different radios, point its antenna different ways. Meanwhile, we're using all the antennas all over the Earth to try to recommand it. So if indeed it happened because Cassini failed in some way, then we, of course, wouldn't hear back. But it would be a long time before we gave up.
We probably wouldn't give up till the end.
My second question is, are you going to start another mission after Cassini ends?
Well, there's another mission in the works to Europa. It's called the Europa Clipper. And so NASA has selected to go back to this other ocean world and to study it and learn more about it for possible future missions. There's even a proposal for a Europa lander to find a place where there might be plumes on Europa, put a lander down on the surface, and sample and look for life coming from that plume. So that's sort of next on the books. I hope there's a lot more. I want to go back to Uranus and Neptune and back to Saturn and Enceladus. So hopefully there's a lot more.
Thank you.
Do you want to read some of the questions?
Let's give
okay.
These two guys
Thank you. Following the goodbye kiss, will you have control over the angle of descent into Saturn's atmosphere? You're saying no, you won't really know the angle?
Well, we will know this one thing. Till the very last second, we'll be pointed the high-gain antenna at the Earth. And that's our goal. And then while we do that, the other axis is pointing the ion and neutral mass spectrometer in the direction of Saturn's atmosphere. So we have picked that orientation. Send back the most data the longest possible time.
The spacecraft will be controlling its attitude until it can't.
I
And
see.
so we will know and it will not only be controlling it, it'll be telling us what it is, again, until it can't.
Would the hope be that it goes in maybe a little more shallow than steep, just to give you a few more
No,
seconds?
it's going in.
It's going in.
It's not going to skip out.
I'm
It's
afraid
not going to
if
skip
it
out.
comes out, we're going to be both very embarrassed and having to deal with a very damaged spacecraft.
Thank you.
I'm not quite sure how to ask this question, but
Great shirt, by the way.
Oh,
Yeah,
thanks.
absolutely. Thumbs up on the shirt.
How do I say this? So there's a lot of talk about the science, but what I'm curious to know is that this is technology that we had 20 years ago, right? When it launched, and so now it's 2017, and so it feels like the analogy that I think of is like a jazz musician. It feels like you're just kind of riffing, and you're kind of just going around and not necessarily making it up, but you have like a hunch and you kind of go for it. Knowing what we know now, like what will we bring to the next jam session, I guess, like what technology has evolved, or what have we learned, or what kind of technology do we wish we had on Cassini that we'll have for Europa Clipper, I suppose. And it's more
Right. Certainly, had we known the potential for life in Enceladus' ocean, if we knew it had an ocean, we would have carried more capable mass spectrometers. That we have mass spectrometers can only look at like 100 atomic mass units, 100 protons worth of molecular size. That's not nearly enough to look for fatty acids, amino acids, evidence for life. So you would carry mass spectrometers, instruments that could do the sampling, that could help answer you're getting free samples, so take advantage, and check it out. And who knows with the camera technologies, our cameras may not be as good as the cell phone cameras of today. So you could do a lot more with the cameras, the spectrometers, all kinds of instruments with the technologies today. And we'd have a lot of more orbit choice, too. We could do skim across the rings, finding this unique orbit. Maybe go inside and come back out. Now that we know it's clear, we could do maybe a lot of things differently. Carry 2 probes, maybe a Titan orbiter, lots you could do.
Okay, great. Well, thank you so much.
You want to? Okay. After this, we're going to ask a couple questions from online.
Okay.
Yeah.
One of the objectives that you named for this final dive is to keep Titan pristine, but Huygens has already gone into Titan. So how was there special protection done, or was it done on the assumption that we weren't going to find as much as we did there?
No, I think that's a fair comment, and we really have to be very careful about Titan's classification. It still is and was what we call a Category 2, which means that the probability of contamination influencing future investigations is very, very low. But nonetheless, Huygens soft landed, and you're absolutely right. It wasn't cleaned any more than Cassini was. It wasn't decontaminated. And so it could have potentially left microbes on the surface. But again, we're bringing plutonium, lots of it, onto the surface, potentially. And again, it's something that we need to take every reasonable precaution to avoid. But Enceladus went from Category 1 or even maybe 0 to Category 3, which means that the probability of our requirements on the probability of inadvertently striking it are much more stringent. And that's really the driver. Titan, at the time, it seemed fine, and you can't undo what we did, and the classification hasn't changed, but it still looks different now than it did.
Right. You could still land on Titan, the way it's categorized now. And in part, the icy crust is so thick above the ocean of Titan, which is where we'd worry about Earth kinds of life, that is so that's why it stayed a Category 2. And there's no direct contact. We don't see any geysers or jets or anything coming out from Titan's surface.
Okay, thank you.
We've got a few questions from the internet. Ocean McIntyre, this is for you, Linda. Are there any suspected reasons for the lack, in fact, they're all for you, any suspected reasons for the lack of dust within the ring gap?
Wow, that's a great question. Why no dust? That's a really good question. We don't know. We're hoping with a few more orbits we can, in a little bit more time, figure that out. But complete surprise. Of all the things we would have guessed, no dust was not even on the list. So.
And then the dynamics for polar activity or inactivity look impressive. Can you elaborate?
Okay, for polar activity.
Airplants Decor asked that. Yeah, about polar activity.
Okay, I think it was probably talking about the hexagon and the vortices, the hurricane-like vortices at the poles. You know, Saturn is spinning, it's mostly gas. We know hurricanes on Earth tend to migrate, you know, toward the poles. They don't ever make it there because they're out of energy. But we have those two hurricane-like features right at the poles. And the energy source for the hexagon for that jet stream, that's a really good question. We're hoping our pictures and new data will help us figure that out.
I think that must be the inactivity references to the stability of that hexagon.
Right. It's been there at least 30 years. Voyager discovered it.
And then here's a good fitting question. AJ asks, will there be a follow-up mission to Saturn in the future?
Oh, I certainly hope so. Saturn to Enceladus,
Absolutely.
Saturn, Titan. There's so much we've left, so many questions that we now have open for a future mission. So thank you very much. Thank you for coming.
Hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Preston Dykes. Well, we are at the end of an era in planetary exploration. In less than 2 days, NASA's Cassini spacecraft will make a fateful final plunge into the atmosphere of Saturn, collecting data until the very last moment as it ends its 13-year tour of the Saturn system. The purpose of our briefing today is to provide background on how we got here with Cassini, along with preparations for the final plunge and some of the science that the Cassini team helps to accomplish as Cassini heads into Saturn. Our participants for the briefing today are, from NASA headquarters in Washington, the director of NASA's Planetary Science Division, Jim Green. Up next, we have the program manager for Cassini here at JPL, Earl Mays. To his left, the Cassini project scientist, Linda Spilker. And finally, team lead for Cassini's Ion and Neutral Mass Spectrometer Instrument, or INMS, from Southwest Research Institute in San Antonio, Hunter Waite. All right, a reminder to reporters dialed in on the phones, please dial *1 to get in the queue to ask a question. And members of the public, as well as the media, can ask questions online via Twitter using the hashtag AskNASA. And with that, let's turn it over to Jim to get started.
Thank you very much, Preston. You know, we're here at a very historic time, but it really started with the Voyagers. Voyager 1 and 2, as we see here in the auditorium, a full-scale Voyager passing through the Saturn system, begging us to go back. And of course, in 2004, Cassini made it to the Saturn system. And as you can see, Cassini, this is a smaller scale model, but if you can imagine the antenna size on Voyager being the same as Cassini, this is a very capable, large spacecraft that has been making fabulous measurements within the Saturn system. My first slide, please. Of course, Saturn, one of the beautiful gas giants in our solar system with the beautiful rings. But studying the planet itself has been incredibly important. The cloud dynamics and the storms that occurred. And in fact, while Cassini was there, a storm that lasted more than 9 months raged in its northern hemisphere. Next slide, please. Of course, as we were able to get to higher latitudes, we were able to look down at the polar region and see other spectacular things. The hint of this hexagon pattern on the North Pole was really observed first by the Voyagers, but we're now back to see that up close and personal. The size of this whole hexagon, which is actually a jet stream on the outer rim of it, is about twice the size of our Earth. In addition to that, we had opportunities to begin to look at the moons. And here, other surprises were well in store for us. As seen in this image, this is Enceladus. This is a small moon just outside the rings of Saturn, and what we thought was an icy ball. When we observed the southern hemisphere in geysers of water spewing out into the Saturn system, it amazed us and began changing the way we view the habitability or potential habitability of moons in the outer part of our solar system. My next image, of course, is the beautiful Titan. This moon is bigger than the planet Mercury. It has an atmosphere twice our atmospheric pressure. If it was orbiting the sun and not Saturn, we would call it a planet. It's truly a magnificent body. The Voyagers could only see the haziness of this beautiful object. But with Cassini, our ability to penetrate through that haze with our radars and seeing what the surface structures and features are, and the Cassini-Huygens probe going all the way down to the surface, revolutionized our understanding of this spectacular moon. This is the only other body in the solar system that has liquid on its surface. Its seas are about the size of our own Black Sea. Now, they're not full of water, but they're full of liquid methane. This is a spectacular world in its own right. Next slide, please. Of course, Saturn has more than 60 moons. Can't see them all, but we saw approximately 24 of them, in addition to Enceladus and Titan. Beautiful moons with all sorts of structures. Those that even, in fact, modify the structure of the rings, creating divisions, or elements that accrete material, and we begin to see all those processes up close and personal. But one of the real stars of the show is Titan. Our ability to fly by Titan, which is about 20 Saturn radii away from Saturn, allows us to use the very basic principle of gravity assist to change the plane of Cassini's orbit, provide new views, and therefore observe in beautiful different ways. The next animation shows you these flybys. Now, what we normally do on flybys is just get a little idea of what that body is. But these flybys have revolutionized our opportunity to use this concept for other missions. We now know from these flybys how to construct a global view of this beautiful world, and we're using it on the Clipper mission that's going to Jupiter and viewing the moon Europa. Cassini has enabled us to make those future missions possible. My next slide, please. Americans had a wonderful view of an eclipse where the moon passed in front of the sun last month. Millions of people appreciate now what eclipses are all about. From our view on Cassini, this is the eclipse, with Saturn moving in front of the sun. This allows, in the low light of blocking the sun, opportunities to see in greater detail the ring structure and other elements. In fact, we were even able to see distant planets and the Earth in a beautiful set of mosaic images that have been stitched together as shown here. That outer ring that you see is called the E-ring. We're able to illuminate it in ways that tells us that Enceladus' geysers of water being spewed out is creating this ring. Now, because of the importance of Enceladus that Cassini has shown us, and of Titan, another potential world that could be habitable for life, perhaps not like we know it, but perhaps completely different than ours. We had to make decisions on how to dispose of the spacecraft. And that led us inevitably to the plan of taking Cassini and plunging it into Saturn. Because of planetary protection and our desire to go back to Enceladus and go back to Titan, go back to the Saturn system, we must protect those bodies for future exploration. Next slide, please. Well, in the visible camera, we've seen more than 450,000 images. Every one of them in their own way are absolutely spectacular. But we made the decision to go through and pick the top 100 images, videos, and animation and create an ebook, something that allows us to go back and view what we accomplished and the beautiful observations that this mission has done. You can download this ebook in several formats at nasa.gov/ebooks. So with that, let's learn how we plan to plunge Cassini into Saturn and what we will learn from that experience. So let me turn it over to Earl Mays, the project manager for Cassini. Earl?
Excuse me. Thank you, Jim. It's been such a unique and incredible privilege and pleasure to operate this spacecraft that before I go into its demise, I'd like to talk just a little bit about some of its many accomplishments. As Jim pointed out, almost half a million images taken, 4.9 billion miles logged on this spacecraft, 635 gigabytes of data played back. Now, that by modern standards is not a whole lot bigger than a flash drive, but you got to think about 80s technology from a billion miles away, and that all of a sudden becomes pretty amazing. We had 162 targeted flybys, and as Jim pointed out, we've been using Titan to great advantage, and there have been 127 of those. Could I have the first graphic, please, just to show you this incredible spacecraft? Now, it's twice again the size of the model in this auditorium if you're here, but it's absolutely splendid, just a built for Saturn. And of course, that's the iconic North Pole of Saturn below it. Now that is an animation. We did not take a selfie stick with us, although those we could have put one on the RPWS antenna in hindsight. That again was something that the 90s didn't know about, so we'll have to live on it. But again, it's just been almost flawless operations in both the instruments and the spacecraft engineering systems, and then the ground support itself, again, has just, I think, made this mission. Not only do we have an environment that just is overwhelming with abundance of scientific mysteries and puzzles, we've had a spacecraft and a team that could exploit it. So again, I will probably come back to that point, but it's just been an amazing, amazing mission. So what are we going to do? Let's get to the last few hours. Could I have the next animation? This is the so-called ball of yarn. What we do, as Jim pointed out, we have a main engine, and it's a great main engine, but we've got Titan, and Titan is a phenomenal main engine. Every time we fly by Titan, we get a little bit better view of Titan, and we get a little bit better view of the Saturn system. Every one of those course changes, every orbit change there is Titan's doing it for us, and it's done for us for 294 different orbits. 127 times we've made major orbital changes, and Titan's been at the center of every one of them. So that's the ball of yarn, and if I could go to the next one, let me just show you what Titan did for us. This was April. All the time we've been outside the rings and paying very, very careful with the rings and with the dust because we really didn't understand the environment well. But for the grand finale, in order to exploit every last ounce of our propellant and the science that Saturn offered inside, we've been in what we've been calling the proximal orbits, or the grand finale. Titan gave us one last little nudge back in April and pushed us, the Cassini spacecraft, between the rings and the planet itself. And we've been skirting back and forth and back from that for 22 times since April. Our last one, unfortunately, was Saturday morning. Or Saturday evening, actually. We got the call back on Saturday morning. We don't normally communicate with the spacecraft during these passages because the science is so precious. We were busy gathering that. So the call home was Saturday morning. We were here, got the call home. The spacecraft's fine. It did it again the way it always has. Monday, we got the kiss goodbye from Titan. 119,000 kilometer altitude flyby from Titan. Took about 39 meters per second of velocity away from the spacecraft. Slowed it down just enough that what's going to happen on Friday is absolutely inevitable. So if I could go to that next animation, just to show this. There is a graphic here. See that Titan flyby? No, that's behind me, I should be pointing. That little Titan flyby was enough to put us into Saturn. It was just distant enough, just close enough, and just the right orientation to seal Cassini's fate. So what's going to happen next? If I could get the next graphic, please. We made contact with Cassini for the last time, I mean, for the penultimate time. We seized contact about 6:50 this morning. After the Titan flyby, we got a call home last night. We were all in the mission support area waiting for telemetry, as it has done over and over again. Cassini came in on time and in perfect shape. It got the flyby that it needed, it got the velocity change it needed, and it's now on its way into Saturn. But before it goes, at about 6:50 this morning, it turned off of Earth back to the job it's been at for the last 13 years, observing the Saturn system. It's going to be taking the last set of pictures of some of the prime targets that it's visited over the many years that it's been at Saturn. And we'll be able to share those with you sometime on Friday. They'll be coming back tomorrow. About 2:45 tomorrow afternoon, Cassini's going to turn back and play back those final sets of images. We figure that to take about 11 hours. So at about 1 o'clock in the morning of Friday, September 15th, we will, the solid state recorders on board Cassini will be empty. And we will then reconfigure Cassini for its very final transmissions. What we're going to do is, Cassini is normally a mission that stores things on data, it's like it's doing right now. We're not in contact. We could look all we wanted, and Cassini's off busy doing its own thing. Stores it on the recorders and then plays it back later. It's doing that right now. But next Friday morning, we're going to turn Cassini into what we call essentially a bent pipe transmission system. Everything that comes from the instruments is going to go right into the recorder and right back out. So there'll be a few seconds delay, but it's essentially now a real-time instrument. And that's to enable the sampling instruments, particularly the ion and neutral mass spectrometer, to get data as deep into the atmosphere as Cassini will permit it. We've taken our data rate down to as low as we can handle so that no matter what antenna we've got on the ground, we'll be able to receive it. So if it's a rainy day in Canberra, in Australia, where we'll be tracked, then we'll be able to have a better chance of getting the data. We've also got antennas both at the DSN tracking stations on the east side of Australia, but also we've got the New Norcia ESA station standing at the ready on the west side. So if we've got a rainy day over the entire continent, well, we're out of luck. But as best we can do, we've got ourselves covered. We will turn at that point also to make sure that the high gain antenna, the large dish you see there, is pointed directly at the Earth. And then we've rotated the spacecraft so that the ion neutral mass spectrometer's aperture is pointing directly into the oncoming atmosphere. So essentially it's getting just a full blast of the atmosphere as it comes in. So how are we going to, the last few minutes? Cassini was not built for atmosphere. As you might imagine, we're a deep vacuum kind of probe. That's not to say it hasn't seen atmosphere. We've flown into the atmosphere of Titan. We've used the thrusters to battle that, the torques and the drag forces that we've had to deal with. And they've been very effective at it. So we know how to fly into a little bit of atmosphere. And we've been doing that for the last 5 orbits. We've actually been dipping our toes down into Saturn's atmosphere for the last 5 orbits. And the thrusters have had to fight back. At what we call a duty cycle, at 100%, they're working as hard as they possibly can. They've been up to into the 40s. So we really have been working the atmospheric effects to some extent. We have a good sense of these. But these are really tiny thrusters. They're built to move a school bus by just kind of tapping it. So they're just not going to be able to do that. I think I'm getting a 1/8 pound. So this is just, you keep touching something, pressing out a little bit, it's about 1/8 of a pound. You can imagine what those thrusters have to do in order to deal with the atmosphere of Cassini. So before I go on to the next animation, let me just point out one final moment here, and at 4:55 a.m. Pacific Daylight Time, loss of signal. And what's going to happen is the thrusters will eventually be overpowered by the atmosphere. We won't watch Cassini burn up. What we'll watch it do is slowly turn away from us, and we'll watch an indicator on the radio science displays that will go down flat and essentially loss of signal. The mission will be over within a minute later. It's going so fast and the atmosphere is thickening so quickly that Cassini will be vaporized in a few, I think maybe 2 minutes, but I think more like 1. So it's just inevitable. It's going in very fast, very steep. Let's go to the next image just for fun to see. There's the timeline of the last 90 seconds of Cassini. Every 10 seconds tick mark there. And that tick mark, as you can see, the final one on my right is, on my left up there, I believe, is where we will lose signal. So you can see very, very tenuous atmosphere, where essentially the analog of that might be on Earth. That's about where the International Space Station is relative to internet density. It's very, very thin air. But Cassini's going so fast, and the thrusters are so modest for this sort of requirement, it's just not going to last much longer. But you can see that about 70 seconds, 60 seconds in, the thrusters are going to start to fight. For the last minute or so, they will be fighting the atmosphere increasingly as it tries to turn Cassini into a more aerodynamically compatible shape. And eventually they will overcome. So if I could see the last graphic, please. This is an animation, and so there's Cassini coming in. This is about that point. You can see we're starting, this is again a bit of a artistic license here. But the thrusters, as you can see down off those extensions on the bottom, are fighting extremely hard to keep the antenna pointed directly at the Earth. And you can see it's going to start to feel the vibration of some of the atmospheric torques. But it will fight, and it will fight, and it will fight. The mass spectrometer is pointing into the atmosphere. The antenna is pointing at the Earth, and it's going to do that for as long as it possibly can. Those of you that have been following this story for a little while might have noticed that we've been a little bit ambivalent about when Cassini's actually going to lose signal. One of the wonders and mysteries of Saturn is that we are always surprised. And we thought we knew what the atmosphere was all about. We had models that told us we were perhaps not going to get enough atmosphere to even satisfy the INMS requirements during the last 5 orbits. We had plans to pop down into the atmosphere. And if it was too thick, we had plans to pop up and pop up again and pop down in order to get this thing fine-tuned. Well, it turned out to be absolutely perfect against all of our predictions. We had all these contingencies planned and we threw them away. But what that tells us also is not only we do not know the atmosphere, but the atmosphere affects when you're going to go in. Every time you go into the atmosphere and get slowed down, well, you go in a little bit earlier. So what started as 5:08 is now at 4:55:06 a.m. Pacific time, and that's our story, and we're sticking to it. So with that, I'd like to turn the mic over to Linda Spilker to tell you about some of the just amazing science that we're going to get in these last few hours.
Well, thank you very much, Earl. Being part of the Cassini mission for the entire mission has been an incredible privilege both for me and for many of the scientists on board Cassini. We've had an incredible 13-year journey around Saturn, returning data like a giant fire hose, just flooding us with data. In fact, if you imagine all that data as a million-piece puzzle, Cassini has been slowly putting together the pieces. We have some of the border, some of the regions, and we're trying to put together the picture of the Saturn system, but we don't have a picture on the cover to guide us, to tell us what that final set of data will finally look like. And what's really great about the grand finale is it's adding incredible new puzzle pieces to help us better understand the Saturn system. And as Earl said, lots of surprises. Many of the things we thought we knew about Saturn are more complicated than we originally had imagined. If we look at the first graphic, this is an example of looking at Saturn from the outside in. That's what we're doing with the grand finale orbits. If you look at that blue figure on your right, that's the auroral oval at Saturn. The particles come in, hit the atmosphere, cause this wonderful aurora. Just underneath it, you have the hexagon with the hurricane inside it. If you look on the bottom right, you can see an image now in the infrared where you can see the heat energy coming out from inside of the planet. And finally, that beautiful image with the hexagon. So we're looking at different levels from Saturn, almost like we've taken a magnifying glass to the planet and the rings. We've also been looking at the interior and, in a sense, pulling back the curtain with our gravity and magnetic field data to see what Saturn is like on the inside as well. Well, as Earl mentioned, we're going to be taking our last images. We hope about 8 o'clock tomorrow night to have the images up on our raw image site if we go to the next graphic. In that last period of time, looking around Saturn, what we're doing is we're taking our final picture postcards of the Saturn system, looking at our favorite targets, and to put these images in our Cassini scrapbook. So we're going to take, if you look at the upper left, a mosaic of Saturn and the rings in color, basically our last look at the entire system. Upper right, that's Titan. We're going to take some goodbye pictures of Titan, last look to see if there's any weather or clouds going on. In the lower left, that's the outer edge of the A-ring, and that bright feature is created by a grouping of particles that we've nicknamed Peggy. We've been watching since 2012 to see if Peggy might break free of the rings and become a moon in her own right. So we're going to take a last look, see what Peggy's up to. In the center, we're going to watch Enceladus set behind the northern limb of Saturn. So very appropriate Enceladus setting. Get a look at the propellers. That's on the lower right, these objects that are trying to open up gaps in Saturn's rings. Not quite big enough to do that, but you can only see those with a spacecraft like Cassini. And then on our final moments of data, we're going to look on the dark side of Saturn at that point where Cassini will be plunging into the atmosphere, looking in the near infrared, the ultraviolet, trying to get some pictures of Cassini's final home inside the planet Saturn itself. Now, if we go to the next graphic, this just came down last night. This is one of our looks at Titan from the Goodbye Kiss. The North Pole, you can see the lake region. We're looking at the North Pole of Titan. Looking through the haze has cleared remarkably as summer solstice has approached. And then if we go to the final graphic, these are the instruments that will be on and sending back data during those final moments with Cassini. And we have 8 of them, including the ion and neutral mass spectrometer, the magnetospheric imaging experiment, the radio science system will be sending back its last gravity measurements, the radio and plasma wave antennas, and then the ultraviolet and infrared spectrometers will also be taking data in that time period, the magnetometer, and the dust analyzer as well. Now, in these very final seconds, we'll be plunging deeper into the atmosphere of Saturn than we've ever gone before. In fact, you can think of Cassini as becoming the first Saturn probe. And to tell you more about sniffing the atmosphere of Saturn, I turn it over to Hunter Waite, and he's the principal investigator for the ion and neutral mass spectrometer. Hunter?
Thanks, Linda. The ion neutral mass spectrometer is actually the sensitive nose of the spacecraft. If we go to the next graphic and zoom in on INMS, you can also see it here. Gas enters into this front portion of the instrument, and inside the molecular composition is determined. And so we have to be pointed in the forward direction, in the direction motion of the spacecraft, as Earl's already indicated. We've done this on many occasions. We've explored the atmosphere of Titan in the same manner. We've explored the plumes of Enceladus with the ion neutral mass spectrometer as well, and found out about the composition there and made some inferences about the internal ocean. And now we get a chance to actually look at the atmosphere that's created in the rings itself and the atmosphere of Saturn. So we're sampling both in this last stage. If you go to the next graphic, there's some idea of the sampling that we're doing. So the 5 dots indicate the 5 previous orbits where we were at the lowest point, or closest to the atmosphere so far. Earlier, we were closer to the rings. And we were close to the rings. There's kind of like 3 bands that we actually sample. So we've had a chance to look more at the ring atmosphere and to look and to progressively see more and more of the atmosphere of Saturn itself. And you can see that line on the graphic that's called well-mixed atmosphere. That's where the atmosphere becomes kind of homogeneous in terms of composition. And we're not going to quite make it to there, but we'll make it close. And in that period of time, we'll be able to make our cleanest sample of the atmosphere of Saturn itself. So if we go to the final graphic, this is a very pretty picture of the rings and of the atmosphere. You can see kind of a haze, which is the atmosphere, just above the edge of the planet. And one of the most important scientific things that we're trying to figure out is a concept called ring rain. And this concept was introduced in the early 80s to actually explain some observations that were made by both Pioneer and Voyager as they flew by. And this particular ring rain was actually water vapor and ice grains from the rings falling into the atmosphere and making modifications to the atmosphere and ionosphere. Well, as Cassini has always delivered, ring rain is much more extensive than that. It's much more complicated. We're getting great new data. We're trying to find out exactly what is coming from the rings and what is due to the atmosphere. And that final plunge will allow us to do that. The other thing that we'll do during that period of time is, as we move closer to the mixed atmosphere, we'll be able to look at some important constituents that we know are there, and we've been measuring them, but we'll get a better idea of the hydrogen to helium ratio. And this is important in terms of the formation and evolution of Saturn itself. So we have an extensive set of science objectives that we're going to execute on this final plunge, and we're looking forward to getting the data in near real time. Thanks. I'll pass it back to Earl.
Thanks, Hunter. After nearly 4 decades of planning, execution, implementation, and execution, we are now within 48 hours of the end of the Cassini mission. The work of 3 space agencies, 17 member nations, hundreds of suppliers, thousands of engineers, scientists, and support staff are about to come to a fiery end high above the clouds of Saturn. The current Cassini team, or family, as it has become, comprised of hundreds of engineers, scientists, and support staff, has worked for many years to bring us to this point, and has done a phenomenal job. As I emphasized at the beginning, this is about a spacecraft and a team that has just been absolutely the best one that could ever ask for in both cases. And it's coming to an end, unfortunately. We'll be saddened, there's no doubt about it, at the loss of such an incredible machine. But I think all of us, we're going to have a great sense of pride in a little bit corny perhaps, but mission accomplished. We set out to do something at Saturn, we did it extremely well, and we delivered more and more. And we've left the world informed, but still wondering. And that's, I couldn't ask for more. We got to go back, we know it. We've been gathering all week, and we'll be staffing up the Mission Control Center tomorrow, standing vigil through the night as we prepare to say goodbye, both from here and a large crowd of our team members at Caltech, as our faithful traveler from Earth makes its final goodbye. So thank you, Cassini, and farewell.
All right. Well, thank you very much to our speakers. It's just phenomenal. We're going to go ahead and open it up for questions, first of all, to reporters here in the auditorium. Please wait for the mic and give us your name and affiliation. Any questions here? We'll start down front.
Thanks. Hi, Irene Klotz with Aviation Week. The last image that's going to be taken from Titan, from Cassini, is it the image of where it's going to impact? And what is the speed that Cassini will be traveling relative to Saturn in the final descent?
I think the answer is yes to the first question. The final image is...
The final image is the place where Cassini will plunge. It'll be dark, but we'll take an image there, yes.
And in miles per hour, we're going about 76,000 miles per hour.
We'll actually have an image with our visual and infrared mapping spectrometer, and that image can sense the heat of Saturn as well. And so we may see some details of the atmosphere in the near infrared.
Thanks. And the 4:55:06, that's Pacific Daylight Time.
Pacific Daylight
what is
time.
the actual time on with the?
It's about an hour and
delay?
21 minutes.
Okay.
It takes the signal an hour and 23 minutes to get from Saturn to Earth. But as far as we're concerned, that what we see is, and what we live with is the signal from Cassini. So when that last signal comes down, that's when things have happened for us.
Okay, another question here in the audience, down front.
Frederick Castell, freelance journalist. 2 questions. When you look at the ephemerides of the different moons, do we see some kind of pioneer effect on the Saturn system? And the other question is on the long term. For next mission, future mission, what's the strategy about plutonium?
I'll start with the pioneer effect, but I'm going to let Jim handle the next one. No, we have not. Because we have so many different perturbations in the system, from the moons, from our own thrusting, from the thermal pressures of the RTGs, even more subtle. We're just too busy perturbing that trajectory to actually be able to see something as subtle as the pioneer effect. It's just too much going on in the Saturn system.
Several years ago, we were able to work with the administration and Congress to get the approval to restart the production of plutonium-238. We've already done a number of tests, and in 2019 we'll get back into the production on a regular basis. We also have approximately 30 kilograms plus of plutonium available to us for future missions. The next plutonium mission that we planned is a Mars mission. It's Mars 2020. But I think we're in really good stead for the next several decades. Our plan is to keep a stock of plutonium and not let that be a mission limiting factor.
Okay, other questions here in the audience? Right here, we'll go inside and then outside.
Hi, thank you for doing this. Will we be able to tell anything from the live stream data on the way into the atmosphere right away? And if not, how long will it be before we know a vague idea of what it's telling us?
That's yours.
Well, the data, the operations team lead for the INMS tells me that she will display it 20 minutes after the time we take it. So we're going to get it streamed to us from the downlink to JPL, be transferred to Southwest Research Institute, and then we'll have it on a computer down in Caltech.
Understanding it might take a little bit longer.
It could, but that's our plan.
Lee Hopes, Wall Street Journal. You mentioned that Cassini has, among its many accomplishments, enabled a series of missions to come. I wonder if you'd expand on that for a moment.
Well, as I mentioned earlier, the concept of the gravity assist that we were able to get with Titan allowed our instruments to get a global view of that beautiful moon. That's really spectacular because that means when we take it to the Jupiter environment where the radiation belt is really harsh all through the area where the Galilean moons are, we want to be able to get in and get out. And so then if we orbit Jupiter, we can do multiple flybys of the moons, and the one we're planning to do is Europa. And from those multiple flybys, actually create a global view of that moon as if we were in orbit. And so Cassini has really pioneered that whole concept, and that will be our next attempt in using that to great effect.
All right, actually, we're going to go to the phones now for a couple of questions, but we'll come back to the auditorium. I think we have Marcia Dunn from the AP. Marcia?
Yes, can you hear me?
Sure.
Yes, for either Jim or Earl or both, there seems to be the outpouring of love for Cassini seems to be growing in these last hours and days. I'm wondering if you had a chance to hear the Cassini opera from the Planetary Society. What did you think about that? And how do you feel hearing from the public who's so sorry to see Cassini go?
I have heard the opera tribute from the Planetary Society, and I loved it. It's very heartwarming to us. As a matter of fact, we've recently posted a letter from a 6-year-old boy who invited us to his Cassini party in Florida on the 15th. The feeling the love, if I may be so corny, is just very heartening because it's part of what we try to do, is to extend everybody out to Saturn. It's not science for, in the ivory tower. It's for humanity, and for everybody to get on ride, come with us, is just phenomenal. So I'm very heartened by that. I wish. Well, never mind. I don't even want to go there. One more orbit. So it is where it is. We've gone this train, and I couldn't be more heartened by the outpouring we've had.
Absolutely. The Cassini family, as Earl mentioned, is those people that have worked many years, decades, to get to this point. And we are absolutely delighted to have an extended family, to share the experiences that have really enabled enormous science to be done. And in fact, really the science is not done until we share it. This is really just the beginning of a number of discoveries that the data will reveal as we try to figure out what the physical phenomena are that are being described in those observations. Those will live on for many decades afterwards, and already they're beckoning us to go back. Between Voyager and Cassini was 30 years. And I believe that will be much shorter the next time around.
Okay, we're going to take a couple of questions from social media. We've got Jason Townsend from NASA headquarters. Jason, what's going on?
Indeed, there's a lot of interest online here. Our first question here comes from Salma on Twitter, who asks, will Cassini completely evaporate in the atmosphere of Saturn, or will it crash into the surface of the planet?
It will be completely vaporized, like many meteorites at Earth. It won't. If there is a surface at Saturn, it's at a hellishly hot and pressure and temperature, and anything from Cassini will have vaporized long before.
Wonderful. Lots of other questions here asking about images here. So Evelyn on Twitter asks, will Cassini be able to take a close-up image of Saturn as it plunges?
No, we don't have the data rate to support sending back images in real time. So the instruments that I showed you did not include the cameras for those final few moments for the plunge. So we'll be getting those images back. The final image will be of the place where Cassini will go, but it'll be from about 14 hours earlier.
All right, next question here comes from Twitter user Billiman, who asks, would it be possible to use a low-gain antenna at a very low bit rate to monitor a heartbeat from Cassini just a little longer?
I'll repeat that for the audience. The spacecraft engineer is in the second row, and the answer is a resounding no. If we'd done that, we would have given up some science data, and really, for a few seconds more to get those last packets of spectrometer data was much more important.
Okay, we're going to go back to the phones. I think we've got Leo Enright from Irish Television. Leo, can you hear us?
Yeah, thanks very much. In fact, my question isn't entirely unrelated to the last one, because I'm wondering, there has been some speculation that a good telescope on Earth, and I presume a really good one, would be able to see this happen. Is that the case?
Well, we're going to try and look with telescopes from the Earth. We're just not sure. This flash will be occurring on the day side of Saturn, and we've done some calculations about brightness. We think it's not very likely, but we're sure going to look anyway.
Okay, one more question on the phones. I think we've got Dave Mosher from Business Insider. Dave, are you there?
Can you guys hear me?
Yeah, we sure can.
All right, great. Actually had a follow-up to the previous question and then one more new one. Do we know which observatories in the southern hemisphere or wherever on Earth are going to be trying to see this thing? That's my first question for whoever can best answer it. And then sort of related to that, but about the data that's coming back, I just checked the forecast for Australia, and it does look like there's a little cloud and rain in the forecast for the next few days. I'm curious if you guys are worried about that at all, or if it's you're confident that you're going to get this data back. Thanks.
Well, the observatories we're going to be using are mostly in Australia. Australia, of course, Canberra has a great view of Cassini. Also, we're going to be using some smaller telescopes. We're going to try and look from India, from China, possibly from Taiwan. We're really encouraging our amateurs, too, to get out there and look with their telescopes. We don't have any giant telescopes in that region where we can see Cassini. So we're just saying, hey, everybody go out, take a look, and we'll see what we see.
We have every confidence that we're going to get the data back. It's going to take a pretty hellacious rainstorm to take out the data. We've got our data rates down at a very low level. If we can maintain the 70-meter antenna, we have a lot of margin. If we do lose the 70-meter dish, then our margin is a little bit lower, but we're still, I believe, comfortable. Worst case, we still have the new Norcia complex over on the other side of the continent that is not really prepared to decommutate our telemetry immediately, but all the data will be on the ground and we can build the right system to take it back apart. So we'll get the data. It's just a question of how soon.
Okay, thanks guys. We're going to go back to social for a couple more questions. Jason?
All right. Twitter user Jason asks, when will a spacecraft visit Saturn again?
That's
so,
Jim.
That's for me. I sort of begged for that question. The observations by Cassini have been so remarkable for Enceladus and Titan that indeed last year we announced the inclusion of those two objects in our focused science program called New Frontiers. Those proposals are in and currently under evaluation, and they do indeed include proposals to go back to Titan and Enceladus. So we'll look through this competition and see what happens.
Okay. You got another question there, Jason?
Sure. This one comes from Pietro, who asks, if you could go back and change something in Cassini, an instrument or skill, what would it be?
Hunter, you want to take that? Okay. If I could go back and change some instruments on Cassini, I think I'd select flying some more capable mass spectrometers. You know, if we had known about the geysers on Enceladus ahead of time, that would have perhaps guided us, something to go back and perhaps look for amino acids, fatty acids, possible evidence of life. So if I could change one thing, it'd be to carry some spectrometers that could do some work for looking for life.
I wouldn't have touched a damn thing. You know, we went in with everything we possibly could. We had the Swiss Army knife, and now we know so much more. Now we can fine-tune it. But this spacecraft, like I said, I couldn't have asked for anything. Anyway, I couldn't have asked for anything more.
All right, we're going to come back to the room. I think Emily, get a.
I'm Emily Loctawalla with the Planetary Society with a couple science questions. Hunter, I'm wondering if you could tell us a little bit more about that ring-rain concept that you're trying to test and what you're learning about it. And Linda, I know that there's a science team meeting going on this week. I'm wondering if you can share any of the early exciting results from the Proximal mission.
Well, the ring-rain concept, as I mentioned, was first introduced in the 1980s. And it was a concept of material from the rings, mainly water vapor and ice grains, descending into the atmosphere and causing changes in the atmosphere. And we have measured that, and we do see the water, but we see other constituents as well. So it's much more complex than we imagined before. And we'll be, you know, we're traveling at 31 kilometers per second, and gas is coming into our instrument very fast and with a lot of energy, and so there's potential to break it apart. And so we're working very carefully to understand that before we go out and tell the public what we're seeing.
Yes, Emily, we're having one of our Project Science Group meetings. In fact, it's the 73rd meeting we were having of this group since we first got started. And there have just been some tremendous presentations about the grand finale science, some of it only days old. And what I can tell you is that many of our models we're finding out are too simple or just out and out wrong. And so the scientists are carefully looking at and calibrating their data and comparing notes and discussing it. And there's nothing that makes a scientist happier than finding out, hey, my model's wrong. I have to sort of start over and work it through. So we have a lot of very, very happy scientists. We're meeting down at Caltech, and so hopefully in the coming months we'll have some answers. But in particular, the interior of the planet is very different than we expected. Its gravity field is not at all what we expected from our models. Also, the magnetic field. We're finding that the rotation axis of Saturn and the magnetic field axis are almost perfectly aligned. And everything we think we know tells us that if you don't have at least a small tilt, you can't maintain those currents that sustain a magnetic field. So we have some more thinking and some more work to do.
Okay, questions here? I think there's one in the third row.
Hi, Robert Perlman with Collect Space. Not that there be any way of verifying this, but has there been any modeling or any even best guesses of how Cassini is going to come apart and what might be the last piece to survive?
Yes, there's been very thorough analysis, piece by piece deconstruction, if you will, of Cassini. And we believe that the final components to be destroyed will be the aeroshell components that are wrapped around. Cassini has these radioactive power supplies, and each little slug of plutonium is wrapped with iridium, and then they're put inside an aeroshell in order to avoid any possible release during a launch accident or reentry. And that's just, the iridium has a very high melting point, and the material around them is even higher. So those will be the last pieces. Other than that, taking those, the parts of the spacecraft that will be shielded away will last a little bit longer, but a lot of the spacecraft is aluminum. It's going to melt very quickly. A lot of it's carbon fiber and mylar and things like that, and they're going to go very quickly.
Okay, how about some more social media questions? Can you?
Sure, here's two good ones here. The first one comes from user Anchel, who asks, what is the last bit of data that we will receive from Cassini?
The very last bit of data will include the ion and neutron mass spectrometer data, but they come down in packets. So we don't know if the INMS packet will be the last one or a magnetometer packet or whatever, but they'll be coming back as quickly as we can send them back. So we'll find out with that final bit.
Well, actually, and we'll see the radio signal dissipate. So our very last bit of science data, if we don't get a complete packet, it could very well be the radio science.
All right, lots of folks are asking about what happens next. So Lisa here says, what happens to the team working with Cassini-Saturn after the missions end? Are they just reassigned to new projects or missions at NASA, or are they off job hunting?
Well, most of the engineers, there is an active planetary program here at JPL, and a lot of our engineers have already kind of half semi-migrated over to these other opportunities. We're not having a big layoffs or anything like that. There's lots of work for everyone. Some of us have some paperwork to do, not just me. So there's a lot of documentation, and of course, the science data, to the extent that it can be funded by research grants, will continue for decades. So those opportunities for both our current and young scientists will be at least for another couple of decades. Got to be.
Right, and the Cassini scientists are funded for the next year, basically to make sure they carefully calibrate and understand all of this grand finale data to put it in the planetary data system. And from there, it will be accessible to future scientists. Who knows how many PhD theses will be written in the coming decades with Cassini data?
So indeed, Cassini's really given everyone on-the-job training on operating spacecraft and keeping our instruments healthy and analyzing the data. And so we have a cadre of highly capable scientists, engineers that will keep busy for many decades. Our planetary program is doing well. We have tremendous support by the administration and Congress. We have missions that we're planning now, and we really have a very bright future.
All right, we've got time for another quick follow-up from Leo Enright from Irish Television. Leo?
I have a question for Earl and Linda about Enceladus, which is a tiny moon, not much bigger than Ireland, I have to point out. And I mean, it's just astonishing that it's so active. Earl, do you have any idea of the chances that Cassini would have actually collided with this tiny moon? And for Linda, really, if you wouldn't mind just telling us, on the scale of things that you've seen in your extraordinary career, I mean, where does Enceladus fit in as the amazing surprise, as it were?
Well, we didn't do the math. Well, actually, I take that back. We did do the math several times for Enceladus, and as long as we could control the spacecraft, no problems. But we had a big challenge in an uncontrolled spacecraft, not hitting within a chance of 1 in a million Enceladus in the next 50 years. The issues are, of course, that once it's uncontrolled, you've got Titan out there pushing it around. It can push you just about, as you saw on those graphics, just about anywhere you wanted to go. And Enceladus was a good-sized target. So we didn't do the actual math for any of those other than to convince ourselves that an uncontrolled spacecraft either had to be well outside of Saturn, I mean way, way outside, or inside.
We have time for one last question.
Well, let me answer the second part.
Sorry,
For Enceladus, I would say Enceladus discoveries made by Cassini are certainly one of the most astonishing set of discoveries for planetary science. To find that there's an ocean world so tiny, with the possibility of life so far from the sun, 10 times further from the sun than the Earth, has opened up our paradigm of where you might look for life, both within our own solar system and in the exoplanet systems beyond. So these ocean worlds, Enceladus, Titan also has a liquid ocean, has really changed our thinking about where to look for life.
Okay, well, I think that's about all the time we have for today for our briefing. Thanks again to our speakers and to all of you for your questions. Here's how you can watch Cassini coverage that NASA television has to offer over the next couple of days. Tomorrow, September 14th, we'll have a speaker program as part of our NASA social event on Cassini from 1 to 2 p.m. Pacific time. That's 4 to 5 p.m. Eastern. Then on Friday, we'll have live commentary from Mission Control from 4 to 5:30 a.m. Pacific. That's 7 to 8:30 Eastern. And following loss of signal, we'll have a post-mission briefing right here, starting at 6:30 a.m. Pacific. You can watch live at nasa.gov/live. More info about Cassini is available at nasa.gov, and you'll find a detailed online toolkit about Cassini's grand finale and end of mission on the mission website at saturn.jpl.nasa.gov/grand finale. And I think we've got a couple more minutes before the end of the hour. We'll end now with a replay of some of the images and video we've shared during our presentation today. Thank you so much for joining us.